De Broglie introduces us to the concept of matter waves. Right? What is De Broglie? What he did was he combined Einstein's theory with Planck's theory. Einstein gave us a relationship between energy and mass. Right? What was that relationship? E is equal to mc squared. And what did Planck give us? Planck gave us a relationship between energy and waves, electromagnetic waves. And he said that waves are made up of particles and the energy can be calculated as h nu, which we can also write as what? hc by lambda. So what de Broglie is saying is that mass has energy, right? And wavelength, electromagnetic radiation also has energy. He combined these two forms. He combined these two things, and he said, what if mc squared is equal to hc by lambda, right? What if mc squared is hc by lambda? So I can cancel out one c. What am I left with? I am left with lambda is equal to h upon mc. Yes, lambda is equal to h upon mc. But this is moving at the speed of light. This is for a particle moving at the speed of light. If I can generalize this for any particle moving at velocity v, I get, generalizing this expression, I get lambda is equal to h upon mv. Now please understand the terms here. De Broglie is saying that if I have a particle of mass m which is moving with a velocity v, this particle will now possess some wave-like characteristics, right? This particle will now also be a wave, and it will have wavelength how much? Lambda. And this lambda which we get here is known as the de Broglie wavelength. This lambda which we get here is de Broglie wavelength. Are you getting it? So a particle of mass m moving with velocity v will have a de Broglie wavelength lambda. Is it okay? So let's calculate this. Tell me, calculate lambda for Usain Bolt. Right. Calculate lambda for Usain Bolt. What is Usain Bolt's mass? Maybe around 80 kilos. Right? This is mass of Usain Bolt. At what speed does Usain Bolt run? Let's approximate that to 10 meters per second. He ran 100 meters in less than 10 seconds, right? So his speed is 10 meters per second, right? So can you calculate lambda? बंद करो यार. किसका फोन बज रहा है? बंद कर. Calculate lambda, please. Calculate the wavelength of Usain Bolt. 8 point. Okay. So calculate lambda as h upon mv, and you got 8.28 into 10 power minus 37 meters. Right? It's wavelength, so it's measured in meters. Right? Now, a very interesting thing to note here is, I have gotten a wavelength. Yes, Usain Bolt, when he runs, he actually behaves as a wave also, and he has wavelength this much. But is this wavelength significant? No. Look at the value. It is 10 power minus 37. ये इतना छोटा है कि इसका कुछ मतलब नहीं है. Right? So this wavelength has no practical significance. This wavelength which Usain Bolt has, 8.28 into 10 power minus 37 meters, it has no practical significance, right? For all purposes, Usain Bolt is a particle, right? We cannot consider him as a wave because the wavelength is insignificant. However, if I ask you this, calculate lambda for an electron in the first orbit of hydrogen atom, let's say. Calculate lambda for an electron in the first orbit of hydrogen atom. Now can you calculate this lambda, please? I'm sure you know how to calculate velocity. We've learned the formula for velocity, 2.18 into 10 power 6 into z by n meters per second. For hydrogenic species, I can get the velocity like that, right? So कितना होगा lambda बताओ? Tell me how much this is. 3 point -13 नहीं, -10 के आसपास आना चाहिए यार. 3.3 Armstrongs, right? Now this value is significant, right? If an electron is behaving as a wave and it has wavelength 3.3 Armstrongs, now this is a significant value, right? We cannot ignore this value because the size of the atom is also in a few Armstrongs. And the electron is moving as a wave with wavelength in a few Armstrongs, right? Now this value becomes important. So this concept of matter waves does not make sense for large objects. But for small objects like electrons, protons, alpha particles, for these small objects, this value is significant. This value is important, right? So what de Broglie is essentially telling us is that the electron, which is revolving around the nucleus, has some properties belonging to a wave. For example, it has wavelength, which means he's saying that the electron is moving something like this. Maybe something like this. De Broglie is saying that the electron is moving as a wave. Right? That's what he's saying. Right? Now this becomes significant. This affects the behavior of the electron. Yes, this is an important value. So, the first formula which we have for calculating de Broglie wavelength is this. Lambda is equal to h upon mv. Mass into velocity is also momentum. So I can also write it as lambda is equal to h by p. Okay? Mass into velocity is momentum. So I can also write it as lambda equal to h by p. Let's start solving a few problems. Please open class assignment 3. Class assignment 3. Please solve question 2. Question 3. Question 3. Class assignment 3. Question 3. Calculate the wavelength of a proton and an alpha particle. It's not L. Please correct it. Question number 3. Compare the wavelength of a proton and an alpha particle. Means the question is asking for wavelength of a proton compared to the wavelength of an alpha particle if both of them are moving with the same velocity. Now if both are moving with the same velocity, right, h is a constant, v is same, so what is wavelength dependent only on? Mass. And how is it dependent on mass? It is inversely related to mass. The wavelength, the de Broglie wavelength is inversely proportional to the mass of the particle. So de Broglie wavelength of proton by alpha particle, can I not write it as mass of alpha particle upon mass of proton? Because how are they related? Inversely. They're inversely related. So I can write it like this. How much is the mass of an alpha particle? 4 AMU. And proton is how much? 1 AMU. 4:1. I hope you know this. Alpha particle किससे बनता है? An alpha particle is 2 protons and 2 neutrons. So it's 4 AMU. And how much is proton? 1 AMU approximately. Yes. So the answer is 4:1. Yes. Okay. Now, I know that half mv square is kinetic energy. Yes. If I multiply and divide with m, mass, numerator and denominator, I will get half into mv whole square upon m is equal to kinetic energy. Yes or no? Right? What is mv? Momentum. So can I not write this as p square upon 2m is equal to kinetic energy? Or I can write that the momentum is square root 2m kinetic energy. I can write this. Right? So another form for de Broglie's equation is what? Lambda is equal to h upon square root 2m times kinetic energy. This is another form for de Broglie's equation. Yes. So solve part B now, 3b. 2:1, right? If kinetic energy is same, then what is wavelength dependent only on? Square root of mass. Because h, 2, ke, ये सब constant है ना? हम पूरा formula क्यों लिखेंगे बार बार? Lambda is inversely proportional to square root of mass. Because kinetic energy is same. So I can say lambda of proton upon lambda of alpha particle will be square root of mass of alpha upon mass of proton, which is square root 4/1. So this is 1. That's all, right? Part C. Do you remember this? If I have a particle being accelerated by a battery of, let's say, 5 volts, or let's say V. V is the potential of this battery, and I have a charged particle Q over here. What will be the potential energy of this charged particle? Q into V, right? And initially, if its kinetic energy is, let's say, 0. If I accelerate it from rest, when it finally reaches here, how much will its kinetic energy be? Q into V. Its potential energy will become 0. So instead of kinetic energy, I can replace that with what? Kinetic energy can be replaced with Q into V, where Q is the charge and V is the potential difference. Please note this V is not velocity. So this formula can also be written as H upon square root 2 m Q into V. We have a third formula. We have a third formula for de Broglie's equation. Lambda is equal to H upon square root 2 m Q V. Mass of particle, charge of particle, and potential difference. Solve part C. 2 root 2 is to 1. Yes. Wavelength of proton by wavelength of alpha particle. Now, if the potential difference is the same, then the two variables are what? Mass and charge. These are the two variables, and they are inversely proportional to square root of mass and charge. So this will be wavelength of proton upon wavelength of alpha particle will be mass of alpha particle into charge of alpha particle upon mass of proton into charge of proton. Now, what is the mass of alpha particle? 4 AMU upon 1 AMU. This we've already seen. What is the charge of an alpha particle? Plus 2. An alpha particle is a doubly charged helium ion, right? So the charge of an alpha particle is plus 2 E coulombs. And how much is the charge of a proton? Plus E coulombs, right? So this is 4 into 2, 8 by 1, right? This is square root of 8 by 1, which is 2 root 2 is to 1, right? Okay, now number 4. Five Armstrong. Yes. So in this case, the value of H is known. H is 6.626 into 10 power minus 34. Mass of an electron we know 9.1 into 10 power minus 31. Charge of an electron we know 1.6 into 10 power minus 19. So what is the only variable here? Potential, right? In this problem, the potential was how much? 6 volts, but that's the only variable. So what I'll do is I'll give you a shortcut. H, M, Q, 2, all these values are known. You can calculate wavelength, the de Broglie wavelength of an electron directly using this result, square root 150 by V. And this will give you directly the wavelength in Armstrongs. Please remember this trick. Okay. So in our given problem, how much was V? How much was the potential difference? 6 volts. So 150 by 6 is 25. Square root 25 is 5 Armstrong. Right? So if you are given any problem, right, where you want to calculate the de Broglie wavelength of an electron, please note, this formula will not work if you have a proton. We have used mass of an electron over here to get this shortcut. Okay? This shortcut is only valid for electrons. Do not end up using this shortcut for protons or alpha particles or some other particle, right? So this is the de Broglie wavelength. This is the de Broglie wavelength for an electron accelerated from rest under potential difference of V volts. V is over here, and this formula gives you directly the wavelength in Armstrongs. Okay, na? This formula directly gives you wavelength in Armstrongs, right? Solve the next question, number 5. यार अगर इतना टाइम लग रहा है मतलब गलत कर रहे हो. देखो, नहीं. I have given you a question where the electron is accelerated using a battery of 4 volts. Okay? But I have given the electron some initial kinetic energy. How much is that? 2 electron volts. Right? This is the initial kinetic energy of the electron. By the time the electron reaches here, what will be its kinetic energy? 4 electron volts it will gain because of the battery. 2 it already had. How much will it be? 6 electron volts. Is it not the same thing as if I accelerated it from rest using a 6 volt battery? Yes or no? अगर इलेक्ट्रॉन का इनिशियल काइनेटिक एनर्जी 0 होता और बैटरी 6 वोल्ट का होता तो काइनेटिक एनर्जी फाइनली कितना होता? 6. So can we not put it in this formula with V6? Answer is 5 Armstrong again. You did not have to solve again, right? This formula is valid for calculating the de Broglie wavelength of an electron which is accelerated from rest under a potential difference of V volts. Right? This is the same situation as if initial kinetic energy was 0 and battery was 6 volt. That would give me the same result. Right? So instead of using 4 over here, what will I have to use? 6. That's all. So answer is 5 Armstrong. Question 1. Does the kinetic energy of an ejected electron, photoelectron, depend on the intensity of light incident? Now this is a question on photoelectric effect. When light falls on a metal plate, right, the maximum kinetic energy of an ejected electron is given by what? H nu minus work function, right, where nu is the frequency of the light which is incident on the plate. Now intensity का मतलब क्या होता है? Intensity means the number of photons which are falling per unit area, or let's say per unit time, that is what is changing. Matlab, let's say initially there were 100 photons falling on the plate per second. When I increase the intensity, what happens is now there are, let's say, 200 photons falling on the plate per second. That is what has changed, right? The frequency has not changed, right? What does this mean? अगर पहले 1 सेकंड में 100 फोटोन गिर रहा था तो लेट्स से 100 इलेक्ट्रॉन निकल रहे थे, अब 200 फोटोन गिर रहे हैं तो 200 इलेक्ट्रॉन निकलेंगे, right? But what will be the kinetic energy of the ejected electrons? That will remain same. That will remain same because I have not changed the frequency. I have not changed the frequency of the light. The energy of one photon is still the same, right? So the kinetic energy of the ejected electron has not changed. The number of electrons which is coming out has changed. अगर मेरे को जो electron निकल के आ रहा है, if I want to increase the kinetic energy of this electron, what do I have to increase? I have to increase the frequency of the incident light. When I increase intensity, I'm not changing the frequency. What am I doing? I'm increasing the number of photons per second. The frequency remains same. So what is affected? If I increase the intensity of light, what happens is the current increases. Because current is what? Current is charge by time. Yes, current is charge by time. And what is charge? Charge is basically the number of electrons which are carrying the charge. Right? Charge is number of electrons. Right? N into charge of one electron upon T. So when intensity increases, what goes up? The number of electrons coming out increases. So as a result, what increases? Current increases. Current increases. But the kinetic energy of the ejected electron remains same. अगर वो increase करना है तो उसके लिए क्या increase करना पड़ेगा? Nu. So just make a quick note. Increasing the intensity of light, increasing the intensity of incident light, increasing the intensity of incident light will increase the current produced, but not influence kinetic energy. Increasing the intensity of incident light will increase the current produced but not influence kinetic energy. Is it okay? If I want to increase the kinetic energy, I have to increase the frequency, not the intensity, right? Intensity से मतलब समझो क्या हो रहा है. Intensity अगर बढ़ा रहे light का तो हम उसका frequency नहीं बढ़ा रहे. कितने photons गिर रहे हैं 1 second में हम वो बढ़ा रहे हैं. That is what is meant by intensity. Is it clear? All right. So that's all for de Broglies. In fact, before I wrap up de Broglie, let me just give you a very interesting observation. What was Bohr's first hypothesis? A very important hypothesis given by Bohr, with the help of which we were able to calculate the size of the atoms, was that the angular momentum of an electron is quantized. That's what Bohr said, right? कि इलेक्ट्रॉन एक ऐसे ऑर्बिट में रह सकता है जहां उसका एंगुलर मोमेंटम क्या होगा? An integer multiple of h upon 2 pi. Right? That was what was marvelous about Bohr's theory. Bohr said that the angular momentum of the electron, MVR, must be equal to nh by 2 pi. This is what Bohr said, right? But when scientists asked him, where did you come by this? ये nh by 2 pi ही क्यों है? nh by 3 pi क्यों नहीं है? Where did you come by this expression? He's like, I don't know. Right? It's the truth. He did not know how he got it, but he knew that the angular momentum has to be quantized, and it will be an integer multiple of h upon 2 pi. Now, this idea, mvr is equal to nh by 2 pi, this is correct, and this was actually confirmed by de Broglie. Let's see how. Dekho, before I get into that, do you understand interference? Have you studied interference of waves? Okay, I'll give you a very rudimentary understanding of interference of waves. Let's say I have a boy here who has a string in his hand, right? And he is creating a wave on this string, right? He's creating a wave on this string. And let's say I have another boy here holding the same string, right? Holding the same string. Now, if this other boy also starts to create waves on the string, right? But he starts to do it like this. He starts to create waves like this. Now, what is happening is, when, let's consider a point on this string. When this boy is trying to take this point on the string and a length down, this other boy is trying to take it by a b length in what direction? Up. So when these two waves superimpose, when these two waves coincide, what will happen is you will end up with a waveform which looks something like this. You will end up with a waveform like this. मतलब it's like this. देखो ये particle को ये wave A ऊपर ले जाना चाह रहा था, and जो दूसरा वाला wave है वो इसको B नीचे ले आना चाह रहा था. So effectively कितना बचेगा? A minus B. अब वो A distance तो ऊपर नहीं जाएगा. Now it will move up by A minus B. This is what we call destructive interference. And when amplitude decreases, this results in a loss of energy, right? So what has happened? The energy of the wave has decreased. On the other hand, if this boy is trying to make the wave go like this, and the other boy is trying to make the wave go like this, right? Now they're both trying to move it in the same direction, right? So the resultant will be what? The resultant will be this. Now the wave will be amplified. The wave will be amplified. What will be the amplitude now? A plus B. This is what we call constructive interference. And that is what is called destructive interference. Whenever destructive interference occurs, the amplitude decreases and it results in loss of energy. It results in loss of energy. Now, the atom, in the atom, the electron is also moving as a wave. Now, if the electron is moving as a wave, let's say like this, 1, 2, 3, 4. This is how it should be. If the electron wave was like this, if the electron wave was like this, what is this resulting in? Destructive interference. अगर ये exactly यहाँ पे up वाला part में नहीं आएगा तो ये क्या होगा? This will be destructive interference and this will result in loss of energy, and because of that what will happen? The electron will lose energy and fall inside the nucleus. But we know that the electron is not falling inside the nucleus, which means that यहाँ से यहाँ तक क्या हुआ? This is one wavelength. From here to here is second wavelength. From here to here is third wavelength, and from here to here is what? Fourth wavelength. Right? The circumference of the orbit must be such that it contains an integer number of wavelengths. The circumference will either be one wavelength, or it will be two wavelengths, or it will be three wavelengths, and so on. It cannot be 3.5 wavelengths, because if it is like this, जैसे ये one wave यहाँ तक हुआ, 1 lambda, this is second lambda, this is third lambda, and then it is 3.5. When you move from here to here, it is like 0.5 lambda or 0.75 lambda, right? This circumference is 3.75 lambdas. But if that happens, that will result in destructive interference, that will result in loss of energy, and that will result in the electron falling inside the nucleus, which is not allowed, right? So in order to maintain the stability of the atom, the number of wavelengths must be an integer number of wavelengths in the circumference. So what de Broglie is saying essentially is that the circumference 2 pi r must be how much? N lambda. Yes? the circumference must be made up of an integer number of wavelengths. Only then there will be no loss of energy. Because एक इलेक्ट्रॉन क्या कर रहा है? इलेक्ट्रॉन जन्मों जन्मांतर तक न्यूक्लियस के चारों तरफ घूमते जा रहा है. It is continuously in that state and it is not losing energy. Even though it is moving, it is not losing energy. Right? It has a fixed amount of energy. So there cannot be destructive interference in its movement, otherwise it will lose energy. Right? So this must be true. Now, according to de Broglie, how much is lambda? H upon mv. Right? De Broglie hypothesis क्या कहता है? Lambda is equal to h by mv. We just solved problems on this. Let's put it here. I get 2 pi r is equal to n into h upon mv. Right? Cross multiply. I take this mv to the left hand side. I take this 2 pi over here. What do I get? mvr is equal to n h upon 2 pi. What is mvr? Angular momentum. And what do we see? It is an integer multiple of h upon 2 pi. So the postulate of Bohr is actually confirmed by de Broglie. Right? De Broglie actually confirmed Bohr's postulate that the angular momentum of an electron must be an integer multiple of h upon 2 pi. होना ही होगा. Yes. So the first orbit will have one wavelength or one wave. The second orbit will have 2 electron waves. The third orbit will have 3 wavelengths. The fourth orbit will have 4 wavelengths and so on. Right? Because 2 pi r is n lambda. N is what? N is the orbit number. So first orbit r1 will have 1 lambda. R2 will have 2 lambda and so on. Right? Heisenberg's uncertainty principle. Write down. Heisenberg's uncertainty principle. Write down. The position and momentum of a particle cannot be accurately determined. The position and momentum of a particle cannot be accurately determined simultaneously. The position and momentum of a particle cannot be accurately determined simultaneously. Right? Now, Heisenberg's uncertainty principle seems very weird at the macro level. It is like saying that if I am moving and you know my momentum, which means you should know my velocity, my mass is definite. So if I'm moving and you know my momentum, Heisenberg is saying that you cannot know my position exactly. There will be some error in your measurement of position. And if you know my position exactly, you will not know my momentum. Right? So essentially he gave us an equation for it. Delta x into delta p greater than or equal to h upon 4 pi. Okay. This is Heisenberg's uncertainty principle. Delta x into delta p greater than or equal to h upon 4 pi. Delta x here represents the uncertainty. Uncertainty means error. ठीक है? कितना हमें error है उसके measurement में, that is the uncertainty here. This represents the uncertainty in position. Delta p represents the uncertainty in momentum. Right? Now we have a very limited scope of Heisenberg's uncertainty principle in our syllabus. ठीक है? हम काफ़ी थोड़ा सा ही पढ़ेंगे. There are many forms of this principle, but we will be looking at only 3 forms which you have to remember. The first is this. Delta x into delta p greater than or equal to h upon 4 pi. Now what is really happening is, देखो, I can write it like this. Delta p is greater than or equal to h upon 4 pi into delta x. Right? Now, if delta x tends to 0, what does it mean? That the uncertainty in position is tending to 0. If the uncertainty is tending to 0, which means that you know the position more and more accurately, right? Which means the position is becoming more and more accurate, right? If delta x tends to 0, it implies the position is becoming accurate. It implies that the position is becoming accurate. What will happen to delta P? It will tend to, if delta x is tending to 0, what will delta P tend to? Infinity. Right? अगर denominator 0 हो जाएगा तो value क्या हो जाएगा? Infinite. Means the error in measurement of momentum is going to be infinite, which is essentially saying that you cannot know the momentum of the particle. Right? Delta P tends to infinity, which means momentum cannot be determined. Right? Which means momentum cannot be determined. Right? Now this seems very strange. Yes or no? But this was actually confirmed and proven experimentally. Okay? Have you guys heard of Walter Lewin? Walter Lewin is a physics professor at MIT, and he has lots of lectures online, right? And in one particular lecture, he explains Heisenberg's uncertainty principle with the help of a laser, right? Now, I don't have a laser. I don't have the equipment which MIT has, right? But I'll tell you what he was doing, and I will send you a link to that video, right? It's a 45-minute video explaining electronic transitions, which we've talked about, as well as Heisenberg's uncertainty principle. Okay? So you will watch that video before next class. Anyway, so I'll tell you what he does over there. He takes a laser, right? This is a circular laser, right? It's a circular beam of photons. It's a laser, and he fires it onto a wall, right? So on the wall, you see this circle, right? This is a laser which you see on the wall. And now what he does is, he places a slit over here, right? He places a slit. This laser is passing through this slit. This laser is passing through the slit, and this slit now he starts to make narrower and narrower. This slit he starts to make narrower. As he is making the slit narrow and narrow, what we know is that we are becoming more and more sure about the position of the particle, right? If the photon is passing through this slit, means how much is the error in its measurement? Delta x. वो या तो इधर से जा रहा होगा या इधर से या इधर से या इधर से इधर से मैक्सिमम इधर से, इसके और बाहर से तो जा नहीं सकता. So the width of the slit is our uncertainty in position. Yes or no? If it is passing through the slit, then the width of the slit is how much the error can be in the measurement of its position, right? We know that for sure कि इसके बीच में से जा रहा है. So the error is only delta x. So what is observed initially is that this starts to get smaller. What is happening? I'm getting more and more accurate the position of the photons, right? I decrease the size of the slit further, right? Let me draw it over here. Let me draw it like this. This is the slit through which the photons are passing, right? Now, if the photons are moving in this direction, they have a momentum vector like this. This is the momentum of the photons. Yes or no? Right? Because they're moving in this direction. Now, this is what this is. This distance is delta x. This distance is delta x. If I increase the accuracy, which means if I make delta x smaller and smaller, the light which I see on my wall will keep getting smaller and smaller. The light will keep getting smaller and smaller. Yes or no? That's what should happen. The light should keep getting smaller and smaller. But suddenly, Heisenberg will come into the picture. Heisenberg is now saying that, hold on, you know the position way too accurately. If delta x has become very small, what can you not know? Delta p. Some inaccuracy in the measurement of momentum is going to creep in. Some inaccuracy in momentum is going to creep in. In what direction? In this direction, right? If delta x becomes very small, then what I have now is some momentum, delta p, in this direction, right? If delta x become very small, then delta p in this direction will start to become significant. So finally, what will the momentum of the photon be? It will be a vector sum of this and this, right? I'm sure you know how to do vector addition. If I do vector addition of this and this, where will the new vector be now? Over here? Or the error could be on this side as well. So the new vector will be what? Over here. So what happens? The photons could be anywhere over here. In fact, that is what really happens also. As I make the slit smaller and smaller, the photons now start to get wider and wider. ठीक है, which is very strange, right? I am making the slit smaller, so the photons should be even more concentrated at a small point, but instead what happens? They start to spread out, which is weird. Yes or no? It goes against our thinking. It is so non-intuitive, right? हम तो साइज छोटा करते जा रहे थे, और फोटोन क्या हो रहा है? और फैलते जा रहा है, right? The photons have started to spread out. The image is now spreading out. Instead of becoming more and more concentrated, it is starting to spread out. Because what is happening? Heisenberg has come into the picture. He's saying, you know the position way too well. You cannot know the momentum that well, right? This is a law of nature. This happens, right? So I'll send you the video to this experiment. You will be able to see this experiment. And this is where Einstein and Heisenberg had a problem, right? Because what Heisenberg is saying is, it is not as if, you know, the slit has got nothing to do with it, right? The slit is made of a metal और उससे कुछ interaction हो रहा है, ऐसा कुछ नहीं है, right? If I take one photon and I pass it through this slit which has been made very, very narrow, then that photon could fall anywhere. Maybe that photon falls here. Then the next photon, maybe it falls here. Then the third photon falls here, fourth photon over here, fifth one over here. I don't know. I don't know. This can keep changing. This can keep changing, right? It's not as if the photon is interacting with some other photons close by, and because of that, this spreading is happening. That is also not the case, right? And this is where Einstein had a problem. Einstein said that if you have certain experimental conditions and you repeat the experiment infinite number of times you should get the same result. You should get the same observation again and again. Only then it is science, right? So Einstein's very famous words are what? That God does not play dice. ठीक है? भगवान के साथ कोई चांस नहीं है. अगर कुछ एक बार हुआ है तो वो बार बार होगा. कितने बार भी कर लो वो वही होगा. God does not play dice. But that is wrong. If a photon is passing through the slit, it could fall anywhere. No one knows where. What we do know is, okay, इसके बीच में कहीं ना कहीं गिरेगा. But कहाँ गिरेगा? That is chance. Right? That is a roll of the dice. It could be anywhere. Right? So that is where, you know, Heisenberg and Einstein had a lot of problems. Because Heisenberg is saying that God does play dice. Where the photon will fall is a matter of chance. We don't know where it is, which Einstein could not digest. Right? You must have heard of these famous words by Einstein that God does not play dice. Right? There is no chance, but there is chance. Okay? And how do we explain it? We explain it by Heisenberg's uncertainty principle. We know the position very accurately, and uncertainty in momentum will creep in. Okay. Now, for the uses of our course, you need to remember three forms of Heisenberg's uncertainty principle. एक ये है, delta x into delta p greater than or equal to h upon 4 pi. The momentum is what? Mass into velocity, right? Momentum is mass into velocity, and mass is a definite value. You understand it? So delta x into m delta v is greater than or equal to h upon 4 pi. I can write it like this. Delta p can be written as m into delta v, where delta v represents what now? Uncertainty in velocity. Delta v represents uncertainty in velocity. Okay? And one quick short derivation. Now, even if you don't understand this derivation right now, it's fine. We know that lambda is equal to h by p, or I can say that p is equal to h by lambda. I differentiate both sides with respect to lambda. Now, you've not learned differentiation yet, but 1 by lambda का differentiation आता है? क्या होगा बताओ? What will be the differentiation of 1 by x with respect to x? नहीं, वो तो integration होता है. What is ddx of 1 by x? ddx of 1 by x is minus 1 by x. ये तुम लोग पढ़ चुके हो क्या? x bar n का differentiation is n into x to the power n minus 1. है कि नहीं? So this is what? This is x bar minus 1. So this is minus 1 into x to the power minus 1 minus 1. That's minus 2. So that's become minus 1 by x square. So same thing over here. I'm differentiating with lambda. So this will become dp by d lambda is equal to minus h by lambda square. dp by d lambda is minus h by lambda square. If I take the mod value, then I get delta p by delta lambda is equal to h by lambda square, or I get delta p, which is the uncertainty in momentum, as h delta lambda upon lambda square. Okay, h delta lambda upon lambda square. If I put it over here, so this is the first form, this is the second form, and if I put over here delta x into delta p के बदले I put h delta lambda upon lambda square greater than or equal to h upon 4 pi, h and h will cancel. I will get delta x into delta lambda greater than or equal to lambda square upon 4 pi. This is the third form. Now there are various other forms where we relate energy with time and kinetic energy with time, etc. But those are not required. Okay? If you remember these three forms of Heisenberg's uncertainty principle, you should be able to get all the problems. ठीक है? And तुम्हारे syllabus में Heisenberg uncertainty बहुत limited understanding में है. And at max तुम लोग को देगा कि uncertainty in momentum इतना है, uncertainty in velocity position बताओ, या uncertainty in velocity इतना है इलेक्ट्रॉन के लिए, उसका uncertainty in position बताओ, बस इतना ही questions आता है. So all you need to remember are these three formula. And for a better understanding, for a much interesting understanding, I will be sending you that link, okay, which you can watch. Right? It's very interesting.
Now you may argue, gee, what difference does it make? Who cares whether something is a wave or whether something is a particle? Well, it makes a huge difference. Because waves have crests and they have valleys. And so if you take two sources of waves, either water waves, two sources, tapping up and down on the water, or you can take two sound sources, then there are certain locations on the surface of the water where the crest of one wave arrives at the same time as the valley of the other. And so they cancel each other out. There is nothing, there's no motion of the water. We call that destructive interference. Of course, there are other places where there is constructive interference, where they support each other. Now, if particles can do that too, that is very hard to imagine. How can one particle with another particle interfere and vanish, that the two particles no longer exist? So if indeed particles are waves, you should be able to demonstrate that by having the interference pattern of two particles like the water waves, and make at certain locations in space those particles disappear, which turned out to be possible. But that's a very non-intuitive idea. So we think of it too classically when we say, well, two particles cannot disappear. But in quantum mechanics, you can think in waves if you want to, and then you have no problems with the interference pattern and the destructive interference at certain locations. Now, there are other remarkable consequences of quantum mechanics in classical mechanics. If you and I are clever enough, you think that we should be able to determine the position of an object to any accuracy that we require, and at the same time determine also its momentum at any accuracy that we require, just a matter of how clever we are. Simultaneously, the object is right there, and that is its mass, and that is its speed. However, the German physicist Heisenberg realized in 1927 that a consequence of quantum mechanics is that this is not possible. Strange as it may sound to you, Heisenberg stated that the position and the momentum of an object cannot be measured very accurately at the same time. And I will read to you Heisenberg's uncertainty principle, the way we know it. It says the very concept of exact position of an object and its exact momentum together have no meaning in nature. It's a profound non-classical idea, and it is hard for any one of us, you and me included, to comprehend. But it is consistent with all experiments that we can to date. I want to repeat it because it's going to be important of what follows. The very concept of exact position of an object and its exact momentum together have no meaning in nature. What does it mean? First, let me write down Heisenberg's uncertainty principle. Delta P, which is the uncertainty in the momentum, multiplied by delta x, which is an uncertainty in the position of that particle, is larger or approximately equal to Planck's constant divided by 2 pi, for which in physics we call that h bar, and h bar is approximately 10 to the minus 34 joule seconds. You see h is 6.6 times 10 to the minus 34. If you divide that by 2 pi, you get about 10 to the minus 34. What does this mean now? Well, it means that if the position is known to an accuracy delta x, and we'll give you some examples, that the momentum is ill-determined, is not determined to the amount delta p larger or equal than h bar divided by delta x. That's what it means. And I'll give you an example which I've chosen from a book of George Gamow. Gamow wrote a book which he called Mr. Tompkins in Wonderland. It's about dreams. Mr. Tompkins wants to understand the quantum world. And there is a professor, you will see a picture of the professor, who takes him in his dreams along the various remarkable, non-intuitive effects of quantum mechanics. And in one of these dreams, the professor suggests that we make h bar 1. And the professor takes a triangle in the pool table, and he puts the triangle over one billiard ball. So the billiard ball is constrained in its position, and that delta x is roughly, say, 30 centimeters, 0.3 meters. That means that the momentum is not determined to an approximate value of 1 divided by 0.3 is about 3 kilogram meters per second. Now, if we give the billiard ball a mass of 1 kilogram, then delta p is m delta v. And so if m is 1 kilogram, then the speed of that billiard ball is undetermined, according to Heisenberg's uncertainty principle, by at least approximately 3 meters per second. 3 meters per second, that means 7 miles per hour. And so that billiard ball will go around like crazy in that triangle. And that's exactly what happens in the dream. And I will show you here a picture from that book. Mr. Tompkins is always in pajamas, just to remind you that it is a dream. And needless to say, the professor is a very old man and has a very nice beard. It adds to the prestige. And I will read you from this book. I will read you a very short paragraph that deals with this. So the professor says, look here, I'm going to put definite limits on the position of this ball by putting it inside a wooden triangle. As soon as the ball was placed, in the enclosure of the hole inside of the triangle became filled up with glittering of ivory. You see, said the professor, I defined the position of the ball to the extent of the dimensions of the triangle. This results in considerable uncertainty in the velocity, and the ball is moving rapidly inside the boundary. Can't you stop it? Asked Mr. Tompkins. No. It is physically impossible. Any body in an enclosed space possesses a certain motion. We physicists call it zero-point motion, such as, for example, the motion of electrons in any atom. So here you see quantum mechanics at work when h bar is 1. This is a very non-classical idea, because you and I would think, and we've always dealt with that in 801, that you can take an object and place it at location A, and we say at time t0, it is at A, and it has no speed, and we know the mass. So we know both the momentum and the position to an infinite accuracy. But according to quantum mechanics, that's not possible. So let's now return to the real world, where h bar is not 1, but where h bar is 10 to the minus 34. And let's now put a billiard ball inside this triangle. Now, delta x is the same, but since h bar is 10 to the minus 34, delta p is of course 10 to the 34 times smaller, and so the velocity is 10 to the 34 times smaller. This undeterminedness, degree to which the velocity is now undetermined, is so ridiculously small, it is 3 times 10 to the minus 34 meters per second, that if you allowed that ball to move with that speed, in 100 billion years, it would move only 1/100th of a diameter of an electron. So it's meaningless again. And so again you see that quantum mechanics plays no role in our daily microscopic world of baseballs and basketballs and billiards and pots and pans. And therefore it is completely okay for us to say, I have a billiard ball which is at point A and its mass is 1 kilogram and it has no speed. That is completely kosher, completely acceptable, and quantum mechanics has no problems with that. Let's now turn to an atom. Take a hydrogen atom. The diameter of a hydrogen atom is about 10 to the minus 10 meters. So the electron is confined to a delta x of about 10 to the minus 10 meters. That means the momentum of that electron becomes undetermined, according to Heisenberg's uncertainty principle, to about 10 to the minus 34 divided by 10 to the minus 10 is about 10 to the minus 24 kilogram meters per second. What is the mass of an electron? That's about 10 to the minus 30 kilograms. So this, delta P, is also m delta V. So it means that delta V, that means the velocity of the electron, is undetermined, according to Heisenberg's principle, by an amount which is at least 10 to the minus 24, which is this delta P, divided by the mass of the electron, which is 10 to the minus 30. And that is about 10 to the 6 meters per second. That is 1/3% of the speed of light. So the electron is moving only because of the fact that it is confined. That's what quantum mechanics is all about. The electron's motion is dictated exclusively by quantum mechanics. I'm going to show you an experiment in which I want to convey to you how non-intuitive Heisenberg's uncertainty principle is. I have here a laser beam, and this laser beam is going to be aimed through a narrow slit. I'll make a drawing. I'll turn this light off. And that slit, which is a vertical slit, can be made narrow and can be made wider. Here is this light beam, and here is this opening, this slit. It's only going to be confined in this direction, not in this direction. And so the light will come out here, and then on a screen, which is going to be that screen, the large distance, capital L, we're going to see that light spot due to the light beam going through the slit. And this separation, capital L. I start off with the slit all the way open. And so you're going to see this light spot like this. And then I'm going to make the slit narrower and narrower. And as I'm going to cut into the light beam, what you're going to see is exactly what you expect. You expect that this light disappears, and when I cut in further, you see exactly what you expect, that this light disappears. And so the light spot there on that screen will become narrower and narrower and narrower. But then there comes a point that Heisenberg says, careful now, because your delta x you knowledge the accuracy in this direction where the light goes through is now so high that now I'm going to introduce an uncertainty in the momentum of that light. The momentum of that light is now no longer determined to infinite accuracy. And what that means, if you start fooling around with the momentum of that light in the x direction, it no longer goes through straight, but it goes off at an angle. And I will make you a more quantitative calculation for that. So let's look at this slit from above. Here's the slit. And the slit has an open delta x. And this delta x we're going to make smaller and smaller. And let us start with a delta x of about 1/10 of a millimeter, which is 10 to the minus 4 meters. I have light. I know the wavelengths of the light. And I know that lambda equals h divided by p, according to de Broglie. I know the wavelengths. I know h, and so I can calculate the momentum of that light. I have done that. Take my word for it. It is about 10 to the minus 27 kilogram meters per second. That's the momentum of the individual light photons. Think of them as particles, which you can do according to de Broglie. So now I have a delta p. The degree to which the momentum is undetermined, according to Heisenberg, is going to be 10 to the minus 34 divided by delta x, which is 10 to the minus 4th. So that is 10 to the minus 30. Very small. But the momentum itself is 10 to the minus 27. So it's only 1 part in 1,000. So what will happen if the light comes through here, and I now make a classical argument. I say this is the momentum of the light as it comes straight in. When it has to be squeezed through this narrow opening, Heisenberg's uncertainty principle demands that it's going to be undetermined the momentum in this direction by roughly 10 to the minus 30 or more. Remember, it's always larger or equal. In other words, if I introduce, for instance, in this direction or in this direction, delta p, then I would expect that some of that light goes off in this direction. It is this change in momentum, this undeterminedness in momentum, that makes it go off in an angle. Only in the x direction. If I have the slit like this, don't expect this to happen in this direction, because the uncertainty in the y direction, that's not the problem. Delta y is not very small, it's delta x that is very small. So it's this direction that's going to give you trouble. It's only in this direction that you know precisely where that light goes through. This direction is not the issue. So this angle theta can now be calculated very roughly. Theta is obviously delta p divided by p. So theta is very roughly 10 to the minus 3 radians, which is a 15th of a degree. And if you have at a distance L, if this distance here is L, if you have here a screen, then the spot on this screen, if I call that x at location L, then x at location L is obviously theta times L. And if theta is 10 to the minus 3, and let's assume this is about 10 meters away from us, so L is about 10 meters, then you get 10 to the minus 2 meters. That is 1 centimeter. 1 centimeter in this direction, and 1 centimeter in that direction. 2 centimeters. But when I make the slit width 10 times smaller, if I make the slit width only 1/100th of a millimeter, then this becomes 10 centimeters. Because now I know delta x 10 times better, and so delta p is 10 times more uncertain. So now I expect to see here at least a smear of 20 centimeters and at least a smear of 20 centimeters there. So the absurdity is that a teeny weeny little light source, which in the beginning you will see as a very small spot, when I make this slit narrower and narrower, indeed you will see that you will lose photons, and you will see this getting narrower and narrower, and then all of a sudden it begins to spread out, and it begins to spread out, and by the time I'm close to 1/10 of a millimeter, the light spot there will be yay big. Very non-intuitive. You make the slit smaller and the photons spread out. And I want to show that to you now. I have to make it very dark. And I need my flashlight. Turn on the laser beam. Yeah. There you see it. The slit is now all the way open. Yeah, it's all the way open. And I'm going to close the slit now slowly. And if you look closely, you will see that let me also get my red laser, then I can point something out. You will see that the light will get squeezed in the horizontal direction. You can see already that the left side has a very sharp vertical cutoff and the right side also. It's getting narrower. It's getting narrower. Getting narrower. But I'm nowhere nearly a tenth of a millimeter yet. It's getting clearly narrower. You see it's getting narrower. It's getting narrower. Now if I look here, oh, I'm not yet at the tenth of a millimeter, but I'm getting there. Going slowly, squeezing it. I'm squeezing those photons. Those photons now are forced to go through an extremely narrow opening. And Heisenberg is very shortly going to jump in and says, you're going to pay a price for that. You know too well where those photons are in the x direction. The price you pay, that nature will now make the momentum undetermined in the x direction. And you see it now. You already begin to see that the center portion is widening. Even photons appear here. You see some dark lines, which I will not further discuss today. But notice that the light is spreading. Of course, when I squeeze this slit, when I make it narrower, it's obvious that I lose light, because the light that hits the side of the slits is not going through. So the light intensity will go down. That's just inevitable. I use fewer photons. But look at this. There are photons here. There are photons there. It's at least 10 centimeters, this portion. From here to here is at least 1 foot. I squeeze more. This is more than half a meter now. I squeeze more. This is about 1 meter already. I squeeze even more. I close the slit now, and I will open it slowly. I'm opening it very slowly, and at the moment that it opens, look at this. You see this? See this wonderful streak? It looks almost like a comet. From here to here is at least a meter. That's that center portion of the light. It has spread out since the poor light was forced to go through this very narrow opening. And now I'm opening it more and more. I'm opening it more. And now, of course, the reverse is happening. Extremely non-intuitive. Now, not only have you seen quantum mechanics at work in terms of electrons jumping between orbits, but you now have also seen one other very interesting consequence of quantum mechanics, which is Heisenberg's uncertainty principle. Now, the spreading of this light can very easily be explained without Heisenberg's uncertainty principle. In fact, it was known, even in the previous century, to a high degree of accuracy, why this happened, and the dark lines were very accurately explained. All I wanted to show is that this spreading of the light is entirely consistent with Heisenberg's uncertainty principle. And it better be, because it would not be possible, it would be inconceivable that you could do any experiment that would violate Heisenberg's uncertainty principle. And if this light that you would see on the screen there, if that light spot would get narrower and narrower and narrower and narrower all the time, as we would think classically, that would have been a violation of Heisenberg's uncertainty principle. And that is not possible. Now, there is no way in advance to predict which photons end up where? All you can do with quantum mechanics is to do the experiment with lots of photons, and then you will get a certain distribution, and the distribution will be exactly as you saw there. Quantum mechanics can never predict on an individual photon where it will end up. We saw that bright spot in the center. So if you did this experiment with 1 photon per day, 1 photon per day going through this slit, and you would have a photographic plate there, and you would keep it there for months, and you would develop it, you would see the same pattern that you see there. This photon arrives today. Here arrives one tomorrow. Here arrives one the day after tomorrow. Here one the day after that. 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 And slowly are you beginning to see that pattern that you saw. So don't think that this interference pattern that you saw is the result of 2 photons going through the slit simultaneously. Not at all. You can do it with 1 photon at the time. And you see exactly the same thing. Now this idea that you cannot in advance predict what a particular photon will do is a very non-classic idea. And it rubs us all the wrong way. Because our classical way of thinking is, and you are no different from my own feeling in this respect, that if you do an experiment 100 times in a controlled way, you should get 100 times exactly the same result. Not so, says quantum mechanics. All that quantum mechanics will tell you is what the probability is that something will happen. No guaranteed, but it is very good in predicting probabilities. Now Einstein had great problems with this idea of not knowing precisely what would happen, and he had endless discussions with Bohr and others in which he tried to convince them that because you couldn't predict what happened, that something had to be wrong with quantum mechanics. And Einstein's famous words were, "God does not throw dice." This was his way of saying it is ridiculous that the outcome of a well-controlled experiment is uncertain. Now almost 9 decades have gone by since the beginning of quantum mechanics, and we now know that God, if there is one, does throw dice. However, God is bound to the rules of quantum mechanics and cannot violate Heisenberg's uncertainty principle. The light could not go straight through without spreading when I made the slit as narrow as I did. So quantum mechanics is a bizarre world that we rarely experience in our daily lives because we are used to basketball, baseballs, tennis balls. But yet, it is the way the world ticks. And atoms and molecules can only exist because of quantum mechanics. That means you and I can only exist because of quantum mechanics. I hope that this will give you something to think about. But I warn you in advance, because if you start thinking about this, it will give you headaches, and it will give you sleepless nights. And it has given me countless sleepless nights in the past, and even today when I think about the consequences, the bizarre consequences of quantum mechanics, I still cannot comprehend it, I still cannot digest it, and I still have headaches and sleepless nights. But it may be necessary to go through these sleepless nights if you want to eventually evolve as an independent thinking scientist, and I hope that someday all of you will. Thank you.
The scientist who combined these theories, his name is Schrödinger, right? We have one scientist saying that no, electron is particle, another scientist coming, no, electron is wave, and then fighting with each other and this and that. And then Schrödinger comes in and he says that matter is both. Matter is particle and wave, right? All matter has wave-particle duality. And he gave us an equation for that as well, which is known as Schrödinger's wave equation. Okay. So let's understand that. Now the solving of Schrödinger's wave equation is outside the scope of our syllabus. I will be giving you a handout today, which is a college level atomic structure, right, where Schrödinger's wave equation has been solved. So for engineering students, some of the points over there will need to be understood. For medical students, basic understanding is enough, but we will be looking at that. Okay. It's very, very interesting. Let's understand. Schrödinger's wave equation is this. dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square uh, m upon h square e minus v is equal to 0. Right? Don't worry about it. This is Schrodinger's wave equation, the solution of which is outside the scope of our syllabus. Dou represents a partial derivative. Psi is the wave function. E is total energy, V is potential energy, etc. E is total energy, V is potential energy, etc. Now, on solving Schrodinger's wave equation, we get what are called orbitals, right? The solution to Schrodinger's wave equations give rise to quantum numbers. Let's start here. The solution to Schrodinger's wave equation give rise to quantum numbers, and these quantum numbers have certain jobs, right? The first quantum number which we get from here is n, small n. Okay. This quantum number n is known as the principal quantum number. This is the principal quantum number, right? And what does it denote? The principal quantum number represents the orbit in which the electron is, right? So if the principal quantum number is 1, then it means that the electron is in the first orbit. So it has values like 1, 2, 3, 4, etc. And this represents the orbit. This represents the orbit of the electron. Then we get another quantum number which is L, small l. This is known as the angular or azimuthal quantum number. Okay. This represents the subshell. Now what we are understanding is that an orbit is made up of subshells, right? There are compartments, think of it in this way, inside the orbit, which are called subshells. जैसे first orbit, second orbit, third orbit, अब उन orbits के अंदर subshells है, right? And that is represented by L, right? The L has a range from 0 to n minus 1, where n is the principal quantum number, right? The values of L can range from 0 to n minus 1, where n is the principal quantum number. So if we find out that L equal to 0, if we find that L is equal to 0, this corresponds to the S subshell. If I get L equal to 0, it corresponds to the S subshell. If I get L equal to 1, it corresponds to the P subshell. If L is equal to 2, it corresponds to the D subshell. And if L is equal to 3, it corresponds to the F subshell. Right? The different values of L correspond to different subshells. L equal to 0 means S subshell, L equal to 1 means P, L equal to 2 means D, and L equal to 3 means F subshell. Right? These are the different subshells. The third quantum number is M. This is known as the magnetic quantum number. This is known as the magnetic quantum number. This represents orbitals. The magnetic quantum number represents orbitals. I'll tell you what orbitals are. The range is minus L to plus L. The range of M is minus L to plus L. Okay. So every value of L will have a range of corresponding values of M. The number of values of M gives us the number of orbitals in that subshell. Write down. Write down. The number of values for small m, the number of values for small m gives the number of orbitals in that subshell. The number of values for small m gives the number of orbitals in that subshell. And next, just write down the definition for orbital. An orbital is a region. An orbital is a region in the molecule, in the atom, sorry. An orbital is a region in the atom where the chances of finding an electron is maximum. An orbital is a region in the atom where the chances of finding an electron is maximum. Okay. Now let's understand this. If n is equal to 1, okay, if n is equal to 1, what is the possible value of L? Only 0. No other value of L is possible because L ranges from 0 to n minus 1. The only possible value is L equal to 0, which implies what? Which implies the S subshell. L equal to 0 implies the S subshell. Now, what are the values of M possible for this? Just one value is possible because M ranges from minus L to plus L. So minus 0 से plus 0 के बीच में कितना value आएगा? एक ही value आएगा, which will also be what? 0. How many values did I get for M? Just one. I got just one value for M, which means this S subshell will have only one orbital. This orbital I will represent with a box. This orbital where the chances of finding the electron is maximum, I will represent with a box. So I will write it as a box like this. And I will write it as 1s. This represents the 1s orbital. 1 is the principal orbit. That's the principal quantum number 1. Where is it? It is in the S subshell, and the S subshell has only one orbital, which I represent as a box. Okay. Next, if n is equal to 2, what are the possible values of L? 0 and 1, because L goes from 0 to n minus 1. So if L is 0, then that corresponds to the S subshell, and if L is equal to 1, that corresponds to the P subshell. Yes. Now, if L is 0, then M का क्या values possible है? सिर्फ एक 0. So I will have only one orbital. This orbital has principal quantum number 2, and the subshell is S. But in case of P, what are the possible values of M? Minus 1, 0 and plus 1. How many orbitals do I have? 3. So the P subshell can have 3 orbitals, and I will represent them like this. The P subshell has 3 orbitals like this. Are you getting it? Right. And this is all which is possible in n equal to 2. If n is equal to 3, what are the possible values of L? It could be 0, 1 or 2. There are 3 possible values. L equal to 0 means what? M equal to 0. L equal to 1 means M will be what? Minus 1, 0 and plus 1. And L equal to 2 means M can have what values? Minus 2, minus 1, 0, 1 and 2. 5 values. Yes. So n equal to 3, L equal to 0, M equal to 0 corresponds to what? 3s. Yes or no? N equal to 3, L equal to 1, and then 3 orbitals. These correspond to what? 3p. Yes, yes. And then this will be what? How many orbitals will I have here? 5. I will have 5 orbitals here, and they will be called what? 3d. समझ आ रहा है कि नहीं? If I have n equal to 4, then I'll have L equal to 0, 1, 2 and 3. Yes. I'll have L equal to 0, 1, 2 and 3. Okay. This represents what? 4s. 4th orbit, S subshell. This represents what? 4p. This represents 4d. Yes. And what will this represent? L equal to 3 means what? F subshell. So this represents 4F. Now for L equal to 3, what are the possible values of M? I have 7 possible values, which are what? Minus 3, minus 2, minus 1, 0, 1, 2 and 3. I have 7 values. So 4F will look like this. Four F will look like this. Yes or no? ठीक है, 4F will look like this. बहुत important है अभी जो मैं पढ़ा रहा हूँ. ठीक है. Now, we have a fourth quantum number S. This is known as the spin quantum number. We have a fourth quantum number S known as the spin quantum number. This spin quantum number has two values. It could be plus half or minus half. The spin quantum number has two values, plus half or minus half, which represent the two spin states, right? So these represent the two spin states of the electron. So write down the two spin quantum numbers. The two spin quantum numbers represent the two spin states. The two spin quantum numbers represent the two spin states of the electron. Full stop. They have no classical analog. They have no classical analog. What do I mean by this? मैं ये नहीं बोल रहा कि प्लस हाफ मतलब क्लॉकवाइज और माइनस हाफ मतलब एंटी क्लॉकवाइज, ये मतलब नहीं है इसका. दो वैल्यू है प्लस हाफ माइनस हाफ, इट मींस दो स्पिन स्टेट्स है, बट देयर इज नो कॉरेस्पॉन्डिंग थिंग कि प्लस हाफ इज फॉर दिस, माइनस हाफ इज फॉर दिस. देयर इज नथिंग लाइक दैट, राइट? सो there are two spin quantum numbers, plus half and minus half. Inside each orbital, I can fill two electrons. And these two electrons, which I fill inside the orbital, will have two spin states. One will be plus half and the other will be minus half. Always. Always. So now, तुम लोग बचपन में ये फॉर्मूला सुने होगे, that max number of electrons in an orbit, what is the formula? 2n square. Yes. So let's now understand how it happens. In the first orbit, how many electrons are possible? 2. I will fill those electrons like this. These arrows represent the electrons. Up arrow means that electron has up spin, and down arrow means that electron has down spin. That's all. Right? How many electrons can we fill in the second orbit? 8. From our formula 2n square, we know it's 8, but now we know better. Now we understand that out of those 8 electrons, 2 electrons go where? In the s subshell, and 6 electrons are where? In the p subshell. That is how they are divided. हम अब ऐसे नहीं समझे कि 8 electrons second orbit, नहीं. The second orbit is made up of 2 subshells, s and p. 2 electrons go in the s subshell and 6 electrons go in the p subshell. Yes. Third orbit, 2 electrons in the s, 6 electrons in the p. How many electrons in the d subshell? 10, because I have 5 orbitals. Each orbital can hold 2 electrons. So I get 10 electrons here. Yes or no? I get 10 electrons here. Yes. Total how much? 18, which you also get from that formula. If I put n equal to 3, this is 3 square 9 into 2, 18. Right? So the third orbit can hold a maximum of 18 electrons. This is 8 electrons. This is 2 electrons. How much can the fourth orbit hold? 32. Right? N square, 4 square, 16 into 2, 32. And how are those 32 electrons divided? 4s can hold how many electrons? 2. 4p can hold 8. Sorry, 4p can hold 6. It has 3 orbitals. 4d can hold how much? 10. And 4f will hold how much? It has 7 orbitals, so 7 into 2, 14. So 2 plus 6 plus 10 plus 14 is how much? 32. Yes or no? ठीक है? Now, these orbitals represent regions in the atom where the chances of finding the electron is maximum. right? So we must know the shapes of these orbitals. Solving Schrodinger's wave equation gives us the shapes of these orbitals, right? So let me draw the shapes. It is important in our syllabus to know the shapes of s, p and d orbitals. इन तीन का shape जानना जरूरी है, f का shape जरूरी नहीं है. I am giving it to you in the handout which I give you today, but that's not part of our syllabus. But s, p and d, you must know the shapes of these orbitals. Let me draw it. So the s orbital looks like this. The s orbital is a sphere, right? The s orbital is spherically symmetrical. So the s subshell and the s orbital are essentially the same thing, because उस subshell में क्या है? एक ही orbital है ना? So the s subshell has only one orbital in it, so that subshell and the orbital are essentially the same thing. It's a sphere. But the p orbitals, how many p orbitals do we see here? 3. The p subshell has 3 p orbitals. These 3 p orbitals are called by names px, py and pz. These 3 p orbitals have names px, py and pz. Px looks like this. This is x-axis, y-axis and z-axis, let's say. ध्यान देना, these are dumbbell shaped orbitals. ठीक है, px looks like this. It is a symmetrical dumbbell, but along which axis? Along the x-axis. Py looks like this. Exactly similar looking dumbbell, but along the y-axis. And pz looks like this. Same dumbbell, but along the z-axis. These are the 3 orbitals px, py and pz. And these regions here, ये जो dotted region यहाँ पे electron मिलने का संभावना सबसे ज़्यादा है. Right? These dotted regions which I have drawn towards the end of the orbitals, we have the maximum probability of finding the electron. Because what has come into the picture now? Heisenberg has come into the picture. I cannot say that the electron is here. I cannot have that certainty. That's not allowed. Right? What can I say? That in this region, most likely the electron will be there. Right? So these are the 3 p orbitals. These 3 p orbitals, px, py and pz, these are called degenerate orbitals. These are called degenerate orbitals because they have the same energy. Degenerate means having same energy. इसको लिख लो, orbitals which have the same energy are called degenerate. Orbitals which have the same energy are called degenerate. Is it okay? Now, how many d orbitals are there? In the d subshell, there are 5 d orbitals, right? Now, the 5 d orbitals, I can classify into 2 types. Okay. They are dxy, dyz and dzx. dxy, dyz and dzx. These orbitals together are known as the T2G orbitals. They are also called the non-axial orbitals. These orbitals together, dxy, dyz, dzx, are called the T2G orbitals or the non-axial orbitals. And dx square minus y square and dz square, these are together called the EG orbitals, and they are axial in nature. they are axial orbitals. ये clear हो जाएगा once I draw the shapes. dxy looks like this. X axis, y axis. This shape is what we call a double dumbbell. dxy has a double dumbbell shape. There are 4 lobes and they are present in the xy plane. This dxy orbital is present in the xy plane and the lobes are oriented 45 degrees to the x and y axis. The lobes are between the axis. That's why we call them what? Non-axial. Right? dyz looks like this. Same shape, but between the y and z axis, and dzx also looks the same. Same shape, but between the x and z axis. Iska 3D diagram I will be giving you as a handout today. Okay. So dxy, dyz and dzx are exactly the same looking orbital, but they are present in different planes. dxy is in the xy plane, dyz is in the yz plane, and dzx is in the xz plane. Straightforward. Okay. Then we have dx square minus y square. Now this orbital looks like this. This is also present in the xy plane. Just like xy, it is also present in the xy plane, but it's oriented along the axis. ये x और y axis के along है ये, इसीलिए इसको क्या बोलते हैं? Axial orbital, क्योंकि ये x axis और y axis के direction में है lobes, right? So this is dx square minus y square, and dz square looks like this. If this is the z axis, it looks like this. Okay. This is called a dumbbell donut shape. This is a dumbbell donut shape, right? Can you imagine a donut? Have you eaten a donut? Right? It's like a ring, right? So imagine a donut, and then in between that we have a dumbbell, right? This is the shape of dz square. These orbitals and their shapes will come in handy in all the preceding chapters, right? Periodic table, chemical bonding, हर जगह ये orbitals और उनके shapes लगेंगे हमें, तभी हम वो theory समझ सकेंगे उन chapters का. So you must understand this well. A lot of things are happening in the atom now. ठीक है? It's not just गोला 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 ऐसे 1 2 3 4. सिर्फ उतना नहीं है, right? There's a lot more happening. The first orbit has the s subshell only. The second orbit has the s subshell, which has the s orbital, and it has p orbitals. The third orbit has s, p, and d orbitals, where it is storing the electrons. The fourth orbital has s, p, d, and f, right? The shapes of the f orbitals are outside the scope of our syllabus. Their shapes and names we will not study. Okay. In our syllabus, we need to know SPD. इतना तो जानना जरूरी है. कितने लोगों के स्कूल में एटॉमिक स्ट्रक्चर हो चुका? तब तो ये सब तो स्कूल में करा ही चुका होगा ना? There's nothing new then. ठीक है? I have not gone any advanced stage पे अभी, ठीक है? We are still in school level, very basic level. ठीक है? So what I need you to visualize is this, that you need, imagine the atom to be a house, right? I don't know if this helps or not, but for some students it helps. Imagine that the atom is like this building, which is something like this, a trapezium shaped building. Huh? Every floor keeps getting bigger and bigger, right? Every floor gets bigger and bigger, right? The first floor has just one room, that is the S room, right? And inside the room there is only one box. This box is the orbital जिसके अंदर हम electron भर सकते हैं, right? The second floor has two rooms, S and P. Now the S room can have only one box, but the P room can have 3 boxes, right? And in boxes के अंदर हम क्या store कर सकते हैं? Electrons. The third floor can have S, P, and D rooms, because now the orbit is bigger, so there's more space, we can have more subshells. In the S I can have 1 box, in the P I can have 3 boxes, but in the D now I can have 5 boxes, right? Then the fourth floor will have S, P, D, and F, right? This has 1 box, this has 3 boxes, this has 5, and this has 7, etc. So as we keep going higher and higher in the orbit, the size of the orbit is increasing. So the number of subshells also increases, and the number of electrons which it can hold also increases in this order. In this order. Is it fine? Okay. Right. Now, if I have an atom and I give you certain electrons to fill in that atom, these electrons will be filled according to a particular rule. And this rule is known as the Aufbau principle. Aufbau principle. Write down. Write down. Electrons are filled. Electrons are filled in an atom. Electrons are filled in an atom in increasing order of energy. Electrons are filled in an atom in increasing order of energy. Right? What this means is कि अगर एक इलेक्ट्रॉन ऐड करना है एक एटम में, तो हम उसको सबसे पहले जो उसका सबसे कम एनर्जी वाला ऑर्बिटल है उसमें भरेंगे. उसके बाद वो ऑर्बिटल जब फुल हो जाएगा तब हम हायर एनर्जी ऑर्बिटल पे जाएंगे, फिर वो भी फुल हो जाएगा तो उसके ऊपर वाला एनर्जी में जाएंगे. इट हैज टू बी फिल्ड इन ऑर्डर ऑफ एनर्जी. So how do we find out which orbital has lesser energy? We use what is called the n plus L rule. Write down. The orbital with lower n plus L value, the orbital with lower n plus L value has lower energy. The orbital with lower n plus L value has lower energy. Full stop. Continue writing. If n plus L value is same, if n plus L value is same, then lower n means lower energy. If n plus L value is same, then lower n means lower energy. Is it okay? So, in the first orbit, I have only one subshell, 1s. In the second orbit, I have two subshells, 2s and 2p. और नहीं हो सकता. In the third orbit, I have 3s, 3p and 3d. In the fourth orbit, I have 4s, 4p, 4d and 4f. In the fifth orbit, I will have 5s, 5p, 5d, 5f. इसके बाद क्या आएगा? 5g. But 5g का elements अभी तक discover नहीं हुआ है. So I'm not writing it. ठीक है? Then we have 6s, 6p, 6d, 6f, 6g, 6h. Not writing. Then 7s, 7p, etc. Right? 8s भी अभी तक discover नहीं हुआ है. Okay, now, which orbital? Achha, before I get into this, I just want to clarify one more concept. The solution to Schrodinger's wave equation is written like this: psi NLM means the three quantum numbers: principal quantum number, azimuthal quantum number, and the magnetic quantum number. Right? They're written together. So if I write, let's say psi 300, right? Which orbital am I talking about? Psi 300, which orbital am I talking about? This is equal to what? Third orbit, because n is equal to 3. L equal to 0 means which subshell? S. So 3s. And उसके लिए m का एक ही value होता है 0. Right? If I, let's say, give you psi 210, what am I talking about? I'm talking about 2, second orbit. L equal to 1 means p subshell. Now, there are three values of m: -1, 0 and +1. So it is convention that m equal to 0 corresponds to pz. It is convention that m equal to 0 is given to the pz orbital. Suppose my question was psi 211. then it could mean 2px or it could also mean 2py. Because plus 1 px py के लिए interchangeably use करते हैं, but m equal to 0 is reserved for z square, is reserved for pz, is reserved for pz. ठीक है? If I ask you this, psi 320, what will it be? 3d and then z square. यहाँ पे भी ध्यान रखना, m equal to 0 is reserved for dz square. The z square के लिए m equal to 0 use करते हैं. बाकी जो है x y y z z x x square minus y square, they can be -2 -1 +1 +2 anything. That is variable. But dz square is reserved for 0. ठीक है? Yes, because that is the p subshell. Here this is the d subshell. The d subshell has 5 orbitals. Out of that, the dz square has m value 0. Right? Now, in an orbital, let me take a sample orbital. Let's say this is 2px, or let's say it is 2pz. Right? Let's say this is 2pz. If I have an electron here, like this, let's say, the address of this electron can be given by the 4 quantum numbers n, l, m and s. Right? इस electron का address क्या होगा? 2. Right? We write it in terms like this, n, l, m, s. This is the address of the electron. So it is 2 because it is in the second orbit. It is in p subshell, so it is 1. Because it is pz, m must be 0. And because it is having upspin, let's say it is plus half. Right? So the other electron in this will be what? Will have what address? 210 minus half. Now, if this electron also had upspin, if this electron was also like this, then what would its address be? 210, this would also be plus half, which is not allowed. Which is not allowed. Okay? Write down Pauli's exclusion principle. Write down Pauli's exclusion principle. No two electrons in an atom, no two electrons in an atom can have the same set of 4 quantum numbers. No two electrons in an atom can have the same set of 4 quantum numbers. Right? Which immediately implies what? It implies 2 things. This will be up, then this has to be down, right? And it also implies that I cannot have a third electron here. If I had a third electron in this orbital, वो या तो ये होता, right? तो उसका और इसका address same हो गया. Or it would be like this, in which case this and this have become same. So this is not allowed. This is not allowed, right? So an orbital can have only 2 electrons, and the 2 electrons which are present in the orbital must have opposite spin. They must have opposite spin. One must be plus half, the other must be minus half. Otherwise their address will become same, and that is not allowed according to Pauli's exclusion principle. No 2 electrons in an atom will have the same set of 4 quantum numbers. For every electron, the set of 4 quantum numbers will have to be different. Is it clear? Okay. So, let's start filling. And now, what you will realize is you will see the periodic table in a whole new light. Okay. Let's see. What is the lowest energy orbital? 1s, right? 1s is the lowest energy orbital. So if I had to fill 2 electrons or 1 electron in an atom, I would fill it in 1s. Right? 1s is the lowest energy orbital. After 1s, what do we have? After 1s, 2s. Because what is the n plus l value? Fatafat batao. 2 plus 0. 2 plus 0. And what is it? This is 2 plus 1. This is 3. So next is 2s. So after 1s, I have in order of energy 2s. Right? After 2s, Now look at these two. They have the same n plus L value. 2 plus 1 is 3. 3 plus 0 is also 3. But which will have lower energy? 2p. If n plus L is same, then lower n means lower energy. So 2p has lower energy, and then I will fill what? 3s. So after 2p, after 2s, first I will fill what? 2p. After 2s, first I will fill 2p, and then I will fill 3s. Next in order of energy is 3s. Okay. Acha, after 3s, now, what will I fill first? 3p. 3p. Because this is 3 plus 2, 5. Sorry, this is 3 plus 1, 4. And this is 4 plus 0, 4. But n plus L is same, so what will I fill first? Lower n. Acha, so 3p pehle fill hoga. Acha, very important. After 3p, I do not fill 3d. Because how much is the n plus L value here? 5. 3 plus 2, 5. And how much is the n plus L value here? 4. 4 plus 0, 4. So after 3p, first I fill 4s. After 3p, first I will fill 4s. So 3s followed by 3p. And then I fill 4s. Because this is 4 plus 0, 4. After 4s, what will I fill now? 3d. अब 3d होगा. देखो third orbit पूरा भरा नहीं था, उसके पहले ही हम fourth में चले गए थे. Right? But now I will fill 3d. Because this is 3 plus 2, 5. This is 4 plus 1, 5. And this is 5 plus 0, 5. So all these three orbitals have the same n plus L. But lower n will be lower in energy. So first 3d, then 4p, and then 5s. Right? So 3d, then 4p, and then 5s. Yes. Right? This is the order of energy of the orbitals. So now tell me, if I gave you hydrogen, right? We'll write hydrogen as 1s1. This is how we will write hydrogen. And we'll represent it like this. This 1 above the s represents the number of electrons in that orbital, or in that subshell rather. 1s1. How will I write helium? 1s2. If I have to fill 2 electrons, I will fill it like this. Yes, this will be helium. Easy, right? What will be lithium? पहला इलेक्ट्रॉन इधर, दूसरा इलेक्ट्रॉन उसमें fill. अब now the 1s is full. So where will I go next? 2s. So lithium will be 1s2, 2s1. This will be lithium. Tell me what will be sodium? I have to fill 11 electrons, right? So what will it be? 1s2, 2s2, then 2p6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then 11th electron will come where? 3s. Yes or no? 3s1. What do you observe? The last electron goes where? In the s subshell. The electronic configuration ends with what? S1. Hydrogen is 1s1. Lithium is ending with 2s1. Sodium is ending with 3s1. So can you guess what potassium will end with? What will potassium end with? 4s1? 4s1? Yes or no? Potassium will end with 4s1. Now, understand, I have to fill 19 electrons. So 1s2, 2s2, 2p6, पूरा भर गया. उसके बाद क्या आ रहा है? 3s2. उसके बाद 3p6, how many electrons have I filled? 10 plus 8, 18 electrons I have filled. Now, after 3p6, what is next? 4s. Very, very important. After 3p6, I have 4s1. Now, as children, you must have studied this. Electronic configuration of sodium is what? 2, 8, 1. है कि नहीं? Sodium used to study as 281. What did you study potassium as? 2881. So 2 electrons in the first orbit, 8 electrons in the second orbit, 8 electrons in the third orbit, and 1 electron in the fourth orbit. कभी सोचा नहीं? Third orbit तो भरा नहीं था. The third orbit was not full. The third orbit had capacity 18. So instead of 2881, why did we not write it as 289? Yes, now you know why. Because before the third orbit is filled completely, I must fill 2 electrons in 4s. Only then I will go to 3d. So potassium is not 289, it is 2881. Now you understand why. समझ आ रहा है कि नहीं? Right? And these elements are all part of group 1. Right? Hydrogen, lithium, sodium, potassium. Can you guess what rubidium will end with? 5s1, cesium will be 6s1, and francium will be 7s1. Right? Elements which are part of the same group will have the same electronic configuration. Yes? So all of these are ending with s1. Right? What about beryllium? अच्छा, by the way, potassium को हम short में क्या लिखेंगे? This entire thing, 1s2, 2s2, 2p6, 3s2, 3p6 is up till argon. Right? This entire thing is the electronic configuration of argon, na? So potassium can be written in short as argon 4s1. This is also a way to write it. Now tell me, what is beryllium? Beryllium is 4. Beryllium is 4. So it is what? 1s2, 2s2. This is beryllium. Yes. What is then magnesium? Magnesium is 12. 1s2, 2s2, 2p6, and then what will it be? 3s2. Yes or no? Right? What will be calcium at 20? 1s2, 2s2, 2p6, 3s2, 3p6, and then what will it be? 4s2. Again, what do they make up? This is group 2 of the periodic table. They end with what? s2. So group 1 ends with s1, group 2 ends with s2. In group 1 and 2, the last electron enters what orbital? It enters the s orbital. It enters the s subshell. That is why they are called the s block elements. Right? Group 1 and 2 are therefore called the s block elements. S block elements तुम्हारा एक पूरा chapter है class 11 में, है ना? Book खोल के देखो कि नहीं chapter के नाम. Right? There is a chapter called S block elements. So now you know why that chapter is called S block elements. कभी सोचा नहीं ये S block element क्या है? Right? So what you will be studying in that chapter is essentially the chemistry of elements in group 1 and 2. That is the S block elements. अब ध्यान दो. Look here. Lithium was what? 2s1. Beryllium was 2s2. After 2s, what do we fill? 2p. After 2s, we fill 2p. Now in 2p, how many electrons can be filled? 6. 6 electrons. So after beryllium, what do I reach here? Boron, group 13. यहाँ से कितना जाएगा? 6. How many electrons can I fill in the p subshell? 6. So I will have 6 groups over here. Boron is 2p1, carbon is 2p2, nitrogen is 2p3, oxygen is 2p4, fluorine is 2p5, and neon is 2p6. The p subshell is full. After 2p6, what do I again come to? 3s1, 3s2, and then after 3s2 again क्या आता है? 3p. So what do I get? 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Right? So group 13 to 18 are called what? The p block elements. Because the last electron enters the p subshell. Right? 3 of those groups are in your class 11 syllabus. The remaining 3 are in the class 12 syllabus. So group 12, 13, 14 is in class 11. And group 13, 14, 15 is in class 11. And 16, 17, 18 is in class 12. Are you getting it? They are the p block elements. Yes. And now, tell me scandium. Scandium is 21. ठीक है? Argon तक कितना हो गया? 18. Till argon it is 18, 288, right? After argon, this is argon, na? Till 3p6 is argon. After argon, what will I have? 4s2 कितना हो गया? 20. Now where will the next electron go? 3d1. 3d1. अब देखो यहाँ देखो periodic table पे देखो. 4s1, 4s2, where have we now come? Scandium. This is 3d1. Now how many electrons can I fill in the d subshell? 10. Before I complete D में 10 इलेक्ट्रॉन भरेंगे उसके बाद ही 4p में जा सकते हैं. So before I reach p, how many groups am I going to find here? 10. These 10 groups which I see here represent the 10 electrons which can be filled in the D subshell. Yes or no? Scandium is D1, D2, D3, etc. up to zinc which is D10. And once 3D10 is filled, हम वापस किस ब्लॉक में आ रहे हैं? P block. 3D के बाद क्या आता है? 4p. Aufbau principle. After 3D, what do we have? 4p. So gallium is what? 4p1. Boron was 2p1. Aluminum was 3p1. So gallium is 4p1. Right? 4p2, 4p3, 4p4, 4p5, 4p6. After 4p, what do we have? 5s. तो इधर आ गए 5s1, 5s2. After 5s, what do we have? Look at the above. 5s के बाद क्या आएगा? 4d. Yes or no? So from yttrium to cadmium is 4d. After 4d, what do we have? 5p means indium to xenon. That's 5p. After 5p, what do we have? 6s, cesium and barium. अच्छा 6s के बाद क्या आएगा? 4f. The n plus l value is how much? 4 plus 3, 7. 5 plus 2, 7. 6 plus 1, 7. 7 plus 0, 7. They all have n plus l value 7, but the lowest n will be lowest in energy. What do we have after 6s? After 6s, we will have 4f. Now 4f can hold how many electrons? 14, because it has 7 orbitals. So after 6s, notice I reach here. ठीक है? Lanthanum. Now ये अलग से लिखा है. From there, here to here, what do I have? I have 14 elements. I have 14 elements from here to here. What are these called now? F block elements. This is a chapter in class 12 called F block elements. जहाँ हम इन compounds, इन elements का reactions पढ़ेंगे. Right? After 4F, देखो ये 57 है, वहाँ पे कितना चला? 71. 71 के बाद 72 देखो वापस इधर आ गया. ठीक है? तो ये जो पूरा lanthanum to lutetium था, ये यहाँ पे है. Are you getting it? Atomic numbers 57 to 71. Then 72 is here. After 4F, what am I filling? 5D. तो ये 5D fill हुआ. Up to mercury. After 5D, what do I have? Again, I'm in the P block. 6P. 6P पूरा fill हुआ radon तक. After 6P, 7S, francium. Radium. After 7S, 5F. So actinide series. From actinium to lawrencium. Right? That is 5F. After 5F, 6D up to copernicium. After 6D, 7P up to ununoctium, 118. Right? उसका अब नाम पढ़ चुका है. I'm forgetting the name of the element. It has been named now. This is an old periodic table. So 7P पे क्या हो गया? खत्म हो गया. यहाँ तक डिस्कवर हुआ है 118 तक. अगला जो आएगा वो क्या होगा? 8S. वो अभी डिस्कवर नहीं हुआ है. That will be 8S1. Right? So that's why. Yes or no? Is it fine? So these two groups, group 1 and 2, are called the S block elements because the last electron enters the S subshell. Group 3 to 12 are known as the D block elements. That is also a chapter in class 12. Big chapter, D block elements. Because the last electron enters the D subshell. Group 13 to 18 are P block elements. And these two, lanthanide and actinide series, are F block elements. समझ में आ रहा है? क्यों एस ब्लॉक में 2 ग्रुप है, क्यों डी ब्लॉक में 10 ग्रुप है, क्यों पी ब्लॉक में 6 ग्रुप है? Because that corresponds to the maximum number of electrons which can be held in that subshell. Yes. Now looking at any atom, you can guess the electronic configuration. Like nitrogen will be what? 2s1, 2s2, 2p1, 2p2, 2p3. If nitrogen is 2p3, then phosphorus will be what? 3p3. Arsenic will be 4p3, antimony will be 5p3, bismuth will be 6p3. Has to be. Are you getting it? Right? Elements in the same group will have the same electronic configuration. Yes? समझ आ रहा है कि नहीं? So scandium is this. Right? Now, certain elements can have some special configuration. Acha, write on manganese first. Write on manganese. Manganese is 25. The first 18 you can short. The first 18 you can compress as argon and then write the rest of the configuration. देखो कैसे लिखेंगे? Manganese is what? Argon. After that 4s2 and then 3d5. Right? Manganese is argon, 4s2 and then 3d5. Now this 3d5 is filled in a particular way. Let's understand. This 3d5 will be like this. And not necessarily just 3d5. Suppose 3d1 is what? 3d1 is scandium, I put over here. Right? Let's say over here. I can put it in any one of these orbitals, by the way. I don't have to necessarily put it in the first one because these orbitals are what? Degenerate. They are of the same energy. Right? dxy, dyz, dzx, इनमें कोई फर्क नहीं है. इन सब का एनर्जी क्या है? सेम. तो मैं किसी में भी लगा सकता था. Are you getting it? Right? I have to make sure that उस energy का सारा full हो जाए, फिर ही next पे जाऊं मैं. Right? So if I have D1, I can place it like this. Right? But let's say I was looking at titanium. Titanium is what? 4s2, 3d2. The second electron, I have to fill like this. Okay? I cannot write 3d2 like this. This is wrong. I cannot write 3d2 like this. This is also wrong. This is also wrong. The second electron must be filled like this. Okay? This is based on a rule which is known as, yes, good, Hund's rule of maximum multiplicity. Write down Hund's rule, please. Write down Hund's rule. Electrons occupying a subshell, electrons occupying a subshell will first singly fill, electrons occupying a subshell will first singly fill each orbital, with parallel spin, will first singly fill each orbital with parallel spin and only then start pairing up. Electrons occupying a subshell will first singly fill each orbital with parallel spin and only then start pairing up. Means, if I have to fill 2 electrons in the D subshell, I will have to do it either like this, or I could also do it like this. This is also allowed. This is also allowed. They will have parallel spin and they will be singly filled. 3d3 कैसा होगा? ऐसा. 3d4 ऐसा. 3d5 ऐसा. Now that every single orbital has been singly filled, 3d6, what can I do? I can now pair. Now I don't have to pair here, I can pair anywhere because they have the same energy. This is 3d6, then 3d7 will be this, and so on. Right? You have to first do what? You have to first fill it singly. हर एक ऑर्बिटल में एक एक इलेक्ट्रॉन पहले भरेंगे, एंड किस तरीके से? पैरेलल स्पिन से. एक नहीं कि एक का प्लस हाफ दूसरा का माइनस हाफ, वो अलाउड नहीं है. They must have parallel spin. Right? And then once all of them have 1 electron each, only then we start to pair them up. So manganese is argon 4s2 3d5. How is this d5 oriented? I will have 1 electron in each of the d orbitals. Is it clear? So tell me this. Write down the electronic configuration of nitrogen for me. Then write down chromium. Then write down copper. Then palladium. Right. What will nitrogen be? 1s2, 2s2. Now they are completely filled, no problem. And then 3p3. How will I fill 3p3? Sorry, 2p3. How will I fill it? Like this. Right? I will first fill every orbital with 1 electron, and they must be with parallel spin. That's essential. Yes? This will be nitrogen. 1s2, 2s2, 2p3. Now chromium will be what? I am writing argon in short. After argon, what should it be? 4s2, 3d4. But there is an exception here. In fact, these 3 are exceptions, which you have to remember. Chromium, copper and palladium, they are exceptions which you have to remember. Instead of being 4s2 3d4, देखो कैसा होना चाहिए था ये? It should have been this 4s2, and then it should have been what? 3d4. Right? Instead of being 4s2 3d4, this atom is 4s1 and 3d5. Instead of being 4s2 3d4, it is 4s1 3d5. 1 electron is sent from S to D, And reason for that, write down, subshells in their half filled, subshells in their half filled or fully filled states, subshells in their half filled or fully filled states have extra stability. Subshells in their half filled or fully filled state have extra stability, right? So instead of being 4s2 3d4, copper is 4s1 3d5. Sorry, chromium is 4s1 3d5. Now copper 29, copper should have been what? Argon 4s2 3d9. It should have been that, but instead of this, what does copper stay as? 4s1 and 3d10. Copper is 4s1 3d10. This is an exception which you have to remember, because the fully filled state of D is extra stable. D9 is not very stable, D10 is very stable, right? Palladium should have been what? Before palladium we have krypton, right? And then krypton, it is 5s2 4d8. It should have been 5s2 4d8. Now ये exception learn करने का है. Instead of this, it is 5s0 4d10. Instead of 5s2 4d8, it is 5s0 4d10. Okay. A rare exception. Is it clear? Yes. 5s0 4d10. Okay. Now, we also understand a concept of magnetic moment. क्या होता है? When charge moves, it creates a magnetic field, right? If electrons are all moving in the same direction, what will they do? They will create magnetic fields, and these magnetic fields will add up, right? But if I have one electron moving clockwise and the other electron moving anti-clockwise, the magnetic fields which they will create will cancel out. So we calculate what is called the spin-only magnetic moment. The spin-only magnetic moment is calculated, and it is written as square root n into n plus 2 bm. The spin-only magnetic moment can be calculated as square root n into n plus 2 bm. Bm is the unit. This is Bohr magnetons. Right. Bm is the unit Bohr magnetons, and n here represents the number of unpaired electrons. N represents the number of unpaired electrons. See, if an electron is paired like this, 1s2, then the magnetic moments will cancel out. So we don't care about them. We don't care about the paired electrons. We only count the number of unpaired electrons. So can you tell me what will be, and we also write like this, that if magnetic moment, spin-only magnetic moment is 0, we say that the atom is diamagnetic. And if it is not equal to 0, we say it is paramagnetic. Okay. If the magnetic moment, which is calculated as square root n into n plus 2 bm, if it is 0, we say that the atom is diamagnetic. If it is equal to 0, we say it is paramagnetic. Clear? So, can you calculate the magnetic moment for iron? Please calculate the spin-only magnetic moment for iron. The atomic number for iron is 26. The electronic configuration is argon. इसके बाद क्या है? 4s2, and then what is it? 3d6. Right? It is argon 4s2 3d6. How will I fill these 6 electrons? 1, 2, 3, 4, 5. And then what will I do to the 6th electron? Now I can pair it. Right? Let's say I pair it here. कहीं पे भी कर सकते हैं. Right? How many unpaired electrons do I have? 4, not 6. Okay. I have 4 unpaired electrons. So the magnetic moment will be how much? Root 4 into 4 plus 2, which means root 24 bm. The magnetic moment for iron is root 24 bm, and we can say that therefore iron is paramagnetic. Iron is paramagnetic because its magnetic moment is non-zero. So iron is paramagnetic. Yes. Tell me then, what about iron plus 2? What about iron plus 2? ठीक है, I have to remove 2 electrons from iron. क्यों सेम रहेगा बताओ? कौन सा 2 इलेक्ट्रॉन जाएगा? हाँ, नहीं, that's the point here. When electrons are lost from an atom, they leave from the outermost orbit first. So Fe plus 2 is argon 4s0 and 3d6. Fe plus 2 is argon 4s0 3d6. कहां से निकला इलेक्ट्रॉन्स? 4s से. ये बहुत इंपॉर्टेंट है. The electrons are first lost from 4s, right? So how much is the magnetic moment still? Same, root 24 bm. तुम same सही आंसर दिए but logic गलत था. The magnetic moment is still root 24 bm. But what if I asked you magnetic moment for Fe plus 3? The third electron is lost from 3d. The third electron is now lost from 3d. So अब ये क्या हो गया? 3d 5. Right? 4s0 3d 5. Now what is the magnetic moment? Root 35 bm. Okay, very important. Fe and Fe plus 2 have the same magnetic moment, but Fe plus 3 has a higher magnetic moment. Right? Root 35 bm. Now this is very important. हम इलेक्ट्रॉन जब भर रहे थे तो 4s को पहले भरे, उसके बाद 3d भरे. बट जब आयंस बनता है तो 4s से पहले निकलता है, because it is outermost. Because it is outermost. So even though it has lesser energy than 3d, it still loses the electrons first. Right? एक और बचपन का झूठ अब सामने आ रहा है. बचपन में पढ़ते थे ना, only the outermost shell takes part in chemical reactions. Iron का fourth orbit is taking part in chemical reactions. Third orbit is also taking part in chemical reactions. Yes or no? In Fe plus 3, what is happening? The s electrons from 4 are lost, and then 1 electron from the third orbit is also lost. So fourth भी part ले रहा है, third भी part ले रहा है. Yes. So ऐसा नहीं होता. ठीक है, ये क्लास 9-10 तक का अंडरस्टैंडिंग ठीक था, that only outermost shell takes part in chemical reaction, but ऐसा नहीं है. ठीक है, 4 भी ले रहा है, 3 भी ले रहा है. Right? Is it okay? Can you tell me what is the magnetic moment for zinc plus 2 then? Zinc is atomic number 30. Please solve. What is the magnetic moment for zinc plus 2? Yes, 0. Zinc is argon 4s2 3d10. All the electrons are paired. This is zinc. So what is the magnetic moment for zinc? 0. But when zinc loses 2 electrons, where are those electrons lost? From s. अब अगर यही तुम अगर डी से इलेक्ट्रॉन लूज कराते तो तुम्हारा आंसर फिर गलत आया था. इलेक्ट्रॉन्स कहां से निकलेंगे? एस से. तो ये क्या हो जाएगा? 4s0 3d10, right? Which means there are still no unpaired electrons. It is 0 bm, which means zinc plus 2 is what? It is diamagnetic. Zinc plus 2 is diamagnetic. Okay. Fe plus 2, Fe plus 3, Fe, they are paramagnetic, right? Very common question in school exams. What is the magnetic moment of chromium? What is the magnetic moment of chromium? Hey? How many unpaired electrons does chromium have? 6 unpaired. 5 in the D subshell and 1 in the S subshell. Right? तो कितना आएगा? Root 6 into 8. Root 48 bm. Right? This is the magnetic moment of chromium. अब if you did not know this exception, अगर तुमको नहीं पता होता कि ये 4s2 3d4 नहीं रहता, अगर तुम इसको ऐसे बनाते तो तुम्हारा आंसर गलत आता. Right? But because you know the exception, you know that the electron is over here. You know that there are 6 unpaired electrons, not 4. Right? So the magnetic moment is root 48 bm for chromium. Okay? This is very commonly asked in school exams in a way to check if you know this exception or not. Is it okay? Any doubts? वो sheet दीजिए सबको. Can I erase the board? Right. Let's now delve a little bit deeper into Schrodinger's wave equation and understand a few more concepts before we end today's class. Right. Now, look at this handout. Okay. Equation 2.53 is Schrodinger's wave equation. Right. They've used reduced mass over there. but equation 2.53 is Schrodinger's wave equation, which I had written on the board. Now what we've done is, from a Cartesian coordinate system, we are migrating to a polar coordinate system, right? Do all of you know polar coordinate system? Instead of x, y, and z, we will be using r, theta, and phi to determine the position of a particle, right? अच्छा board पे देखो, फट से एक second लगेगा. If let's say this is x, y, and z axis, and I have a particle here, right, whose coordinates are x, y, z, right? Now instead of using x, y, z, I want to use different parameters to define its position, right? The distance of this particle from the origin is, let's say, r, right? The angle it makes with the z axis is theta. The angle it makes with the z axis is theta. So what will be the z component of this distance? Sorry, let me write it like z, this is x, and this is y, right? The angle it makes with the z axis is theta, right? So what will be this component? R cos theta. ये तो अब तुम लोग फिजिक्स में काफी कंफर्टेबल हो चुके होगे, वेक्टर्स वगैरह पढ़ चुके हो. This is r cos theta. So the z component, the z essentially is what? R cos theta. And if I project it in the xy plane, this r, it makes theta with the z axis. So in the xy plane, how much will this be? अरे ये एंगल 90 डिग्री है ना, तो अगर ये r cos थीटा है तो यहां पे क्या होगा? r sin थीटा है कि नहीं यार? इमेजिन करो ये पंखे के ये पे r है ये, राइट? This is the origin. From origin to that fan is r. So on the z axis, this angle is theta. So its projection, its component along the z axis is r cos theta, and its component on this side will be in the xy plane. Its component on this side will be in the xy plane. That will be how much? R sin theta, right? So the component of r in the xy plane is r sin theta. This component, let's say, makes an angle phi with the x-axis, right? So how much will be the x component then? R sin theta cos phi. R sin theta cos phi. And what will be the component along the y-axis? R sin theta sin phi. R sin theta sin phi. That's what we've done, right? So instead of using x, y, and z, all the x's will be replaced with r sin theta cos phi, all the y's will be replaced with r sin theta sin phi, and all the z's will be replaced with r cos theta. तो देखो ये जो बॉक्स करके बना रखा हूं मैं, वहां पे वही है ये. Instead of z, I will use r cos theta. Instead of x, I will use r sin theta cos phi, and instead of y, I will use r sin theta sin phi, right? I'm transitioning from a Cartesian coordinate system to a polar coordinate system. This is better for me because I want to talk about the center of the atom as the origin. I want to talk about the nucleus as the origin, and then I want to locate the electron in the atom. So rather than x, y, z, it's better to have r theta phi. Yes? Yes. So equation 2.55 at the bottom of the page, that is what Schrodinger's wave equation becomes when we convert it into the polar coordinate system, right? Now solving this equation, ये तुम लोग बाद में सीखोगे, page turn करो, right? Solving of this equation is outside the scope of a syllabus. We will directly see 2.56, right? On solving Schrodinger's wave equation, we get the wave function psi, right? Now this wave function has two components essentially. One is the radial component r, जो इस r के terms में है, and then there is the angular component, which is theta and phi, right? First is the radial component, and then we have an angular component from this solution. Now, if you look at table 2.1, that gives you the various values of n, l, and m, which we've already studied. N equal to 1, L equal to 0, m equal to 0 is 1s, right? And अगर तुमको असली solution चाहिए, जो हम shapes बनाए हैं, right? The s orbital has a spherical shape, the p orbital has a dumbbell shape. So for those shapes, you can see the equations of those shapes in table 2.2. Look at table 2.2. इतना आगे क्यों चलेगा यार? साथ में रहो ना, right? Look at table 2.2, page 39. Right? If you see that table, that is giving you the real shapes. Now in engineering exams, JEE वगैरह में ये equations आता है, ठीक है? You don't have to remember these equations, but you should be able to observe these equations and gather information from it. For example, look at the equation which you have for 1s, right? In that you notice that there is a variable q in the radial part of the solution. The radial part of the solution has the variable q, but the angular part of the solution, does it have any variable? No, it is a constant, 1 upon 4 pi to the power half. That's a constant, which means the orbital does not depend on angle. There is no theta या phi का term, right? So the orbital does not depend on angle, and this is what also the shape is telling you. The shape is what? The shape is spherically symmetrical. No matter at what theta or phi you are, the orbital is same, right? So 1s has no theta or phi term in its solution. Look at 2s also. There is no theta or phi term, right? The angular part is constant, but look at 2px, 2py, and 2pz. There are theta and phi terms. There are theta and phi terms in the solution. So ये 2018 advance में आया था that this orbital, this equation represents which orbital. So you did not have to learn the equation, you just had to observe it. Yes or no, right? Look at the equation for 3s. Look at the angular part again. What is it? Constant again. Because again, the s orbital is a spherically symmetrical orbital. It does not depend on angle. Theta और phi पे depend नहीं करता. ठीक है? So बाकी सारे orbitals का भी equations दिया हुआ है यहाँ पे, right? Now, the radial distribution function, right? The radial distribution function, it essentially represents the probability density. अच्छा ये थोड़ा सा क्या होगा? ये जो radial part है ना, इसको I can plot with radius. जैसे इसका ग्राफ बना सकते हैं. I can make a graph of R versus R. ठीक है? And if you see now, figure 2.10, look at these graphs. These graphs are very, very important. The first graph came in 2017 mains. First question was the first graph over here. Okay? These graphs are important. We have to understand them. Now the first graph is the graph for 1s. It looks like this. Right? This is the graph for 1s. Now, what this graph represents is a probability density. Right? R squared, square of this graph will represent a probability density. जैसे if I have mass density, बोर्ड पे देखो, if I have mass density rho, density is what? Mass by volume, right? So if I multiply density with volume, what do I get? Mass. So if I had probability density, and if I multiplied with it volume, what would I get? Probability. I would get probability. Instead of mass density, if I have probability ka density, then if I multiply that with volume, what will I get? I will get the probability, right? So what I'm doing is, pay attention, I am taking a shell. I have, let's say, a sphere of radius r, and outside it, I have another sphere of radius r plus dr, right? Imagine a sphere of radius r, and then another sphere of radius r plus dr. So what I have is a very small shell, a very, very thin shell. What will be the volume of this very thin shell? It will be some very small volume dv. What will that be? 4 by 3 pi r plus dr cube minus 4 by 3 pi r cube, right? This will be approximated to 4 pi r square dr. Now ये कैसे होता है ये हम अभी नहीं देखेंगे, right? But this is approximated to 4 pi r square dr. This is volume, and when I multiply this volume with r square represents the probability density. So when I multiply r square with dv, this essentially tells me the probability of finding an electron, right? R square into dv essentially gives me the probability of finding the electron. And now इसी के बगल में देखो तुम्हारा फिगर में भी ग्राफ बनाया हुआ है, r square versus r, right? Square of the radial part of Schrodinger's wave equation multiplied by r square proportional to the volume, right? So this gives me the probability of finding an electron. So what am I doing here? Let's say, ध्यान दो, let's say ये 1s, let's say this is the 1s orbital, ठीक है? If I take this volume and I multiply it with the probability density, I should get the probability of finding the electron in this tiny volume. I should get the probability of finding the electron in this tiny volume. And I keep making this shell larger and larger. So when the shell was at the nucleus, what was the probability of finding the electron? 0. Yes. Now as I make this shell larger and larger, as I approach towards the orbital 1s, what will happen to the probability of finding the electron in this small shell? It will keep increasing. And then after I go outside this 1s, what will happen to the probability of finding the electron? It will again decrease. So ये ग्राफ कैसा दिखेगा? This graph will appear like this. This graph is the probability of finding the electron as you keep increasing the radius of the shell. Right? So जैसे जैसे तुम ये शेल बड़ा करते जाते हो, इलेक्ट्रॉन का मिलने का संभावना in this small shaded region keeps increasing till it reaches a maximum. Right? And then if you become bigger, more bigger than that, what will happen? The probability will now start to decrease. So this distance r, where the probability of finding the electron is maximum, this is Bohr's radius, A naught. This is what Bohr had told us, right? So what Bohr gave us was not the distance, exact position of the electron. What Bohr told us was the position where the chances of finding the electron was maximum. This is Bohr's radius. Now, in the second graph over here is for 2s. The second graph over here is for 2s, right? And 2s के लिए ये वाला ग्राफ देखो. 2s के लिए ये वाला ग्राफ देखो. Now 2s यहाँ पे कहीं है. Let's say this is 2s, right? Now if I'm drawing the probability graph, I'm drawing this one for 2s, r square versus r, right? As I keep increasing this shell, what will happen? The chances of finding the electron is increasing till it reaches a maximum over here. When I reach the orbital 1s, the chances of finding the electron is maximum. Then as I keep moving further, what will happen? What is happening to the chances of finding the electron? It is decreasing. Decrease, okay, यहाँ तक आएगा, right? And then as I move further away, what will happen? It will start to increase again. And then once I reach 2s, it will be a maximum. And then as I move away from 2s, what will happen? It will again start to decrease. So this graph is going to look like this. This maxima is the point where I reach the 1s orbital. And then धीरे धीरे क्या हो रहा है? वापस कम हो रहा है probability electron मिलने का. फिर as I am approaching the 2s, what is happening? The chances of finding the electron is increasing again. When I reach 2s, it is again maximum. When I cross 2s, what happens? It again starts to decrease. Now in between 1s and 2s, there is a region over here, which I'm marking in blue. This region has zero probability of the electron being present. This graph touches this axis, means the probability of finding the electron is what? Zero. What are these points called? School में तो पढ़ाया जा चुका है. What are these points called where the chances of finding the electron is zero? What is this point called? It's a node. This is a node. Right? And this is what we call a radial node. A radial node is a sphere. ठीक है? This is a radial node. Are you getting it? अगर 3s होता तो उसमें कितने radial nodes आते हैं? 2. Look at the graph. Look at the graph. What do you notice? For 3s, the probability graph is touching the x-axis twice. For 3s, the probability graph is touching the x-axis twice because it will have 2 nodes. Right? The first node will be between 1s and 2s. The second node will be between 2s and 3s. These are spherical nodes. So write down the definition of a node. Write down the definition for a node. A region in the atom where the probability of finding an electron is zero. A region in the atom where the probability of finding an electron is zero. Right? So this here, these points where the probability graph touches the x-axis, they represent the nodes. जहाँ electron मिलने का chance क्या है? Zero. Right? Now another type of node which we have in atoms are called angular nodes. Now I'll give you a formula which will come in very, very useful when you're solving problems. Number of radial nodes for any orbital you can directly calculate. Number of radial nodes is n minus l minus 1. कोई भी orbital लो, उसका n और l value तुमको पता ही है अब. The number of radial nodes is given by n minus l minus 1. You can use this directly to solve problems in school. The number of angular nodes is given by simply L. So the total number of nodes for any orbital, total number of nodes is how much? N minus 1. Very important. You must remember this formula. I'm showing you. As the name suggests, it also is a region in space where the chances of finding the electron is 0, right? Now, say I have px, right? If I have px, for px, how much is the L value? L is 1. So for a px orbital, we will have one angular node. The angular node for px looks like this. If this is the x-axis, y and z, px is this. The angular node for px is the yz plane. Right. The yz plane is the angular node for px, because any point on this plane will have 0 chance of finding an electron, because this plane does not touch the orbital at all. है कि नहीं? तो इस प्लेन पे कोई भी पॉइंट होगा, वहां पे इलेक्ट्रॉन मिलने का चांस क्या है? 0. Right? So the angular node for px is the yz plane. Similarly, if I asked you for py, the xz plane, yes, right? This plane, this is the x, this will be the node, the angular node for the orbital py. So for py, the xz plane is node. And this is what we call an angular node. An angular node is a plane or some other surface. A radial node is a sphere. Radial node is sphere. Angular node can be plane or some other surface also. Okay. What about dxy? L is equal to 2. For dxy, L is equal to 2. dxy looks like this. X-axis, y-axis, and the shapes you know. Can you tell me what are the two angular nodes? Can you tell me the two angular nodes? And zx is correct. Zx will look like this. This is an angular node. What else? yz. ऐसे भी काट सकते हैं. Right? I can cut it like this, and no points on these planes will have chances of finding the electron. So the two nodes are xz plane and yz plane. So I have two nodes. They are angular nodes. Yes? For dxy, I will have these two planes. Similarly, dyz, dzx अपने आप कर सकते हो. What about this? What about dx square minus y square? This is x-axis, this is y-axis. Can you identify the nodes here? नहीं, xz तो ऐसा होगा, ये तो ऑर्बिटल को कट कर रहा है. What will be the nodes over here? It will be at an angle. It will be a plane like this, which is at 45 degrees. And it will be another plane like this, which is again at what? 45 degrees? Yes or no? It will be a plane like this, which is 45 degrees to the x-axis. And it will be another plane like this, which is 45 degrees to the y-axis. Yes? You will learn how to calculate the equations of these planes later on. ठीक है? Maths में coordinate geometry में 3D geometry है तुम्हारे syllabus में. Right? So when you study 3D geometry, you learn how to calculate the equations of these planes as well. But these will be the planes. Yes or no? It will be an inclined plane like this. Okay. dz square. ये जो आंसर करेगा उसको मेरी तरफ से ट्रीट. Can you imagine a nodal for the dz square orbital? Can you imagine a surface, a nodal plane, where the chances of finding the electron is 0? ऐसे इसका कोई नाम थोड़ी हुआ यार. Yes? Think 3D, think 3D. It has two planes, it has two angular nodes, because what is L? D orbital means L equal to 2. The number of angular nodes is always equal to L. So how many angular nodes for 1s? 0. Right? Or 2s has how many angular nodes? 0, because it is spherically symmetrical. L is equal to 0, so it has no angular nodes. But this has two angular nodes. No. The sphere will intersect. If I draw a sphere over here, maybe it is not intersecting the donut, but it will intersect the lobe. It will intersect the dumbbell. Yes or no? It will touch the dumbbell now. Like this. It's a cone. Can you imagine a hollow cone? Yes? If I have a cone with a vertex at this point, it will not touch the donut. neither will it touch the lobe. So one cone pointing upwards, one cone pointing downwards. Yes, these two cones will be the angular nodes for dz square. Can you visualize this? Right? ऐसा है, ये cone है, ये ऐसा hollow cone. Yes, this is an angular node for dz square. Is it okay? So in general, अगर तुमको कोई ऑर्बिटल दे दे, ठीक है, तुमको जनरली ये शेप्स वगैरह नहीं पूछेगा, इन सब का शेप्स पूछ सकता है जितना मैं बताया हूं, इससे ज्यादा और कॉम्प्लिकेटेड शेप्स नहीं पूछा जाएगा. एंड यू हैव टू रिमेंबर दैट फॉर्मूला. ठीक है, जैसे एक सिंपल एग्जांपल लेते हैं. सपोज आई गिव यू 3p. सपोज आई गिव यू 3p. हाउ मेनी रेडियल नोड्स? बताओ, हाउ मेनी रेडियल नोड्स? n minus l minus 1 means 3 minus 1 minus 1. For p l equal to 1, so how much is this? 1. Look at the radial node graph for 3p. Look at the graph for 3p in figure 2.10. How many times is it touching the x-axis? Once. Because it has one radial node. How many angular nodes? Equal to L, which is 1. So total nodes for 3p is 2. So 3p has one radial node and one angular node. But if I had 3D, how many radial nodes for 3D? Yes, it is 3 minus 2 minus 1, n minus l minus 1. This is how much? Look at the graph. Is it touching the x-axis? Right. The graph which I have given you in figure 2.10, the number of times that graph touches the x-axis represents the number of radial nodes. Okay, na? Right. If you turn the page, you can see the various shapes which I had drawn beautifully over there in 3D. Okay. 1s, you can see a spherically symmetrical orbital. 2p, you can see the 3 dumbbell-shaped orbitals. You can see the 5 d orbitals, dxy, dyz, dzx, dx square minus y square, and dz square. On the next page, you can also see the 7 f orbitals. Okay. Those shapes are not required. जो 7 f orbitals है, ये हमारे syllabus में नहीं है. Are you getting it? Those names and those shapes are not required for us. ये थोड़ा सा advanced हो गया, but इसके पहले का सब कुछ चाहिए. हाँ, all this we need. Is it okay? One last thing, we also calculate orbital angular momentum. Orbital angular momentum is given by the expression under root L into L plus 1 h upon 2 pi. ऐसा क्वेश्चन आ सकता है, कैलकुलेट द ऑर्बिटल एंगुलर मोमेंटम फॉर एन इलेक्ट्रॉन इन 3p. सो फॉर p, l is equal to 1, so you just put in the values over here. Right? So orbital angular momentum, this important formula, is square root L into L plus 1 h upon 2 pi. We can calculate orbital angular momentum from here. And another important thing to remember is that all orbitals in a hydrogenic species, all orbitals in an orbit for hydrogenic species are degenerate. All orbitals in an orbit for hydrogenic species are degenerate. मतलब 1s है, ये तो अकेला ही है, but next क्या है, 2s और फिर 2p. If I have hydrogen, then for hydrogen all these 4 have the same energy. In hydrogen, all these 4 have the same energy. Means the degeneracy of hydrogen in second orbit is how much? 4. 2s is lesser in energy than 2p in multi-electron systems. मतलब जो Aufbau principle हम पढ़े थे, वो कब valid है? जब एक से ज़्यादा इलेक्ट्रॉन होता है. अगर एटम में एक ही इलेक्ट्रॉन है, तो 2 के सारे ऑर्बिटल्स क्या होंगे? सेम एनर्जी. राइट? तो कितने सेम एनर्जी के ऑर्बिटल्स होंगे? 4. सिमिलरली 3 अगर हुआ, हाइड्रोजन का थर्ड ऑर्बिट में क्या होगा? 1 plus 3, 4 plus 5, 9. So all the 9 orbitals will have same energy. All the 9 orbitals will have same energy. उनमें कोई फर्क नहीं होता. Right? तो हम ये एनर्जी डिफरेंस वाला कब पढ़ते हैं? Aufbau प्रिंसिपल कब एप्लीकेबल है? In multi-electron systems. In a single electron system, Aufbau principle does not work. All orbitals in a given orbit are degenerate. They have the same energy. ठीक है ना? So all orbitals in an orbit for hydrogenic species are degenerate. Right? बंद कर दीजिए.